minutes. Okay, so let's see. So I can give you. Il resto è uguale che era tu, perché proprio it should be fine, right? USB-C. Yes, it should be. Um, we'll for 15 minutes. We'll ask the speakers to come and prepare at the end of the previous speaker's talk so that we can roll down quickly. And our first speaker for today is Toby Haas, that will tell us about quantum features from classical entities. Please. Thank you, Robin. So, for those of you who don't know me, I'm currently a postdoc in Bonn in Matzkin School. But most of the stuff talking about today has been done before when I was with some people that said and the main idea of today's talk is that you're all using all quantum information recursive by and then you should be one point to make all these kind of things
But in many experimentally relevant scenarios, we can take inequalities, especially with these original comments.
Sorry if I interrupt you. So should I use both now?
That one.
Okay.
So
Okay. Okay. If you want to learn anything about what I'm going to be talking about, I recommend the theory people to look into this one, and the people who are more interested in experimental applications in the paper that's going to be appearing in PRL letters soon, but of course it's on the archive already. All right, so the motivation and the idea is quite simple and general. Namely, let's say we are interested in understanding the information structure of a complex system. A very simple example is you take a one-dimensional system and want to know how does the information in a subregion, so basically an entropy associated to a local state, depend on how big the interval is. Now, this question has been answered for many, many theories. Namely, if you calculate the entanglement entropy as function of system size in one dimension, you find that for ground states of locally gapped Hamiltonians, you get what is known as the area law. Of course, we know something like the area law also from black holes. And in general, you expect it in ground states or in quenched states. Of course, the area law is not typical at all. A random pure state will follow a volume law. And this happens, for instance, when you look at a thermal state, which is, of course, rather common in experiments. At the same time, if you quantify the correlations between A and B via the quantum mutual information, you will find lots of correlations in the area law case and not so many in the volume law case. Now, this is all well known, well studied in many body systems, QFTs, whatever. But how would you actually measure it, show it? It's not that easy as soon as the system is complicated, or if the local Hilbert space dimension is large, which is the case, for instance, for bosons. Now, what could you do? If you still have a small and controllable system, you could do state tomography. Fine. There are some clever readout techniques for spins or in an optical lattice where you really just have a few particles. LOL. Okay, sorry. Or you simply abandon information measures and say, we just want to learn about correlations. But of course, this is extremely unsatisfactory, and people have for a long time thought about, can we somehow access the quantum information content also in more complicated systems? And the question we're gonna ask today is, in order to do that, do we actually need quantum entropies and the local state? Can we also start from something that is way more common in an experiment, namely a probability distribution associated with a measurement? This directly leads to the idea of classical entropies. So in any experiment, you are usually dealing with some types of fundamental degrees of freedom, the observables. In the case of a scalar field, it's just the field operator and the conjugate momentum field operator. And if you measure one of them, then it's really similar to quantum mechanics, i.e. a single mode. You don't get something like a probability distribution over a single variable deposition, but instead a high-dimensional probability density over all the many-body constituents, or in the field theory limit, you actually get something like a probability density functional. Now, this is what the experiment gives you, and of course, if you're interested in local information, you just trace out the degrees of freedom you're not interested in, meaning you integrate them out. Now, if we are super naive and just consider the classical entropy associated with this, what do we get? And when I say classical, I mean Shannon-like entropy. Well, because the fundamental degrees of freedom are often non-commuting, these entropies are subjected to the uncertainty principle. Remember, entropies can be considered as a measure of how localized a distribution is, and we cannot arbitrarily localize a distribution over the field and the momentum field at the same time. So what you find is that there is a state-independent lower bound by the vacuum state. And with vacuum, I mean that in the many-body picture, every single mode is in its vacuum state and there are no correlations at all. Now I'm telling you that this entropy is finite for each single oscillator. And since you have a product state, the total entropy is, of course, just something like a volume law. Okay, but if the uncertainty principle tells us that any classical entropy will always scale with volume, how can we ever learn anything? How can it be that an area law should emerge? And the super simple idea we had is we just consider the difference between, let's say, the left and the right side of the uncertainty relation and define the subtracted classical entropy. So we just subtract the leading order volume law contribution and study this type of entropy. The funny thing is, if you would do the same for a mutual information, you would find that you don't have to subtract anything because you subtract here, but if you subtract here and using that everything is additive for the vacuum, it just cancels out. Now, the interesting thing is that if the distribution you're interested in is over non-commuting observables, then it actually immediately encodes quantum correlations in a very similar way than quantum entropy does. Namely, if the state is separable, then something like the conditional entropy is non-negative. Also, if we start from a globally pure state, then any classical mutual information is necessarily zero. So it's clear that there has to be some quantum information in there. The question is now how much and how close is it related to an actual quantum entropy. So let's consider a very simple example, namely the free quantum field which has this Gaussian Hamiltonian with some mass. Well, if you compute a typical distribution, so for example, the one over the fields or the momentum fields, you will find that, and again, this is very similar to a single harmonic oscillator, you will get something like a Gaussian distribution corresponding to a ground state, characterized by two-point correlation functions in the covariance matrix. And if you're interested in excited states, which in the QFT represent particles, you get something like the polynomial. This is very similar to Hermite polynomials for a single oscillator. And if you do the calculations, which takes some time, you find that the entropy essentially has a Gaussian part and a non-Gaussian part, which can be computed very similar with similar techniques to Feynman diagrams, only that you need some sort of directions as well. This is just to say you can do the computation. So let's see what comes out. Right, so if we consider the ground state, what are typical measurement distributions in an experiment? Well, for instance, you just measure over the field configurations. In a phase space picture, this is something like the marginal distributions in phase space. There are some setups, for instance, in quantum optics, where you also have access to the Wigner distribution or the Husimi distribution. All of them carry some type of information over the underlying state, of course. And what we find is that for any Gaussian state, any of these subtracted Rényi entropies of the Wigner is simply equal to the Rényi 2 entropy, so the purity of the reduced state. Therefore, we see immediately that the classically subtracted entropy encodes everything that the quantum entropy does as well for Gaussian states. Now for the ground state, we also have that the Wigner distribution factorizes, and this becomes a sum, meaning that if you just have access to, let's say, the field, or in a many-body sense, to all the individual positions, then also this is immediately related to a quantum entropy. And if you actually calculate and plot the subtracted classical entropy for all these 4 distributions, you will find for all of them area laws with different prefactors than the normal one for the phenomenon entropy. Because for phenomenon entropy, we have 1/3, For Wigner, we have 1/4. For these two, we have 1/8. And for Q, it's a bit more complicated. Okay, so the subtracted classical entropies behave as quantum entropies. They show the area laws. And the question is now, how can we use all of this in an experiment? We made a proposal based on the capabilities in Heidelberg in the group of Markus Oberthaler, and they have a spin 1 BC, so a very complicated system, in particular a system where all the methods we have to directly measure quantum entropy do not work. They have the following types of dynamics. It's a spin 1 BC, meaning they have 3 hyperfine levels. And in each of the hyperfine levels, atoms are colliding all the time, and you have a split due to the second order Zeeman shift. Additionally, they can take 2 spins in the 0 eigenstate and pump them to plus and -1, which is just spin collisions. And because we want to have a many-body problem, we are doing this on 20 of those small BCs and couple them one to the other. What they can read out in the experiment, and we just consider the 5 wells in the middle of a 20-well system, are spin operators. And you can think of them as something like a canonical pair, at least for early times. For entropy estimation, we use the unbiased K&N method. I wish that this is something that would be way more known, because compared to machine learning and so on, it's simply totally unbiased, meaning it converges very fast. And you estimate the entropy directly from the data and make no assumptions on the state. So this is really what we want, right? Okay, here are the results. If you do a quench, so start from uncoupled vacuum, at early times, all entropies and mutual information are 0. And then slowly, area laws start to appear. This straight line here is to show that this is not linear, but indeed something logarithmic. All of these curves are fits. And you really see that quantum correlations are generated by the area law. At later times, we expect the system to thermalize, and this is something we see as well, because these curves start to tend to a linear line, which is not changing anymore. And the good thing is, by the incline, we get the temperature for free. All right, I also show a video of this whole thing just for the Wigner quantities. All right. So basically exactly what you would expect for the entanglement entropy, but now for something you can actually measure. Let's summarize. I'm motivated to use subtracted classical entropies whenever you cannot measure the quantum ones, which applies to more or less all quantum many-body systems. So in case anybody is in this audience and wants to know, can I use it in my system as well? The answer is yes, and please do so. We considered a scalar field and saw that the ground state area law emerges for all typical distributions you can get. On the experimental side, we considered a spin 1 BC, a very complicated system with lots of different dynamics, estimated the entropy using an unbiased estimator without any assumptions on the state, and observed exactly what you would expect, namely area to volume law transition. So the take-home message is, if you want to understand from an information theoretic perspective quantum phenomena, then you may want to have a look at classical entropies. And just to mention a few applications, Lieb-Robinson bounds could be derived for them. You can think about extracting topological entanglement entropy in central charges. Symmetry resolution, one big thing we are currently working on with the group of Silke Weinfurtner and Jörg Schmidtmeyer is to actually do it with experimental data or even use it in analog gravity. My last slide is a small advertisement for those of you who don't know. I started a seminar series which is Q Meets. We are inviting always a duo of scientists, usually an old guy and a young guy, to talk in a broad fashion about a nice physics results. So if you're interested, just check out our webpage, Q Meets. Thanks for your attention.
Well, we have time for maybe one very quick question. And the next speaker sets up.
Okay.
Yeah.
Want to keep this? No, thank you. Okay.
Okay. But next speaker is Alex Lamponi. He'll tell us about please take the stage.
Thank you very much. Thank you, Fabio, for your nice introduction. Yeah, I'm Alessio Lapponi, a fourth-year PhD student in cosmology, space science, and space technology, even if my main research field was always been on relativistic quantum information, in particular to communication. Yeah, today I want to talk about this novel approach that I had in mind. I'm honest, I would like to present more results, but I had not enough time. So I decided to structure this talk in the following way. I would like to start from a paper that I published in January, and from there explain to you why from this paper we can probably find a novel approach for particle production by using communication between particle detectors. However, yeah, so I'm not presenting this talk aims not to present the results for the paper, but most of all to give you this idea, and then the core of the talk will be the interaction that I will have with you afterwards during coffee breaks or question time. So yeah, the paper. Basically, the paper consists on the communication between two Unruh-Dewitt detectors with infinite energetic levels, so harmonic oscillator detectors, interacting with a massless scalar field. The interaction occurs in particular with a delta-like switching in function. Then we are talking about obviously bosonic states, since the detectors are harmonic oscillators. If the input is a Gaussian state, also the output will be a Gaussian state. This means that the channel is a one-mode Gaussian channel. In general, how to evaluate the capabilities of a quantum channel? Well, the capabilities to transmit, for example, classical information are quantified by this quantity here, which is the classical capacity, which in case of two harmonic oscillators interact with a massless scalar field is proportional to this ratio here, which is basically the ratio of the imaginary part of the two-point Weizmann function, and in the denominator instead we have the real part of the same point Weizmann function. Yeah, this is the protocol setup. Now the background. Obviously, since we have to compute the normal modes of the field, the classical capacity will be sensible to the background space-time it lies on. I'm considering a cosmological expansion, so the metric will be the Friedmann-Lemaitre-Robertson-Walker. In particular, we need at least one point in time which we can take as a reference to say, okay, in that point, the modes are Minkowskian, and then we propagate with perturbation theory, we know how the modes are afterwards. In so doing, it's like we are choosing a time, in particular the time where Alice, so the sender, interacts with the field, and we approximate this time as the one where the spacetime is Minkowskian, let's say, or approximately Minkowskian. By doing that, basically, we are neglecting what happened before. It's like any prior cosmological expansion is not considered. What are the results? Well, classical capacity turns out to be equal to that, where f is this parameter, which we consider to be always positive. It could also be negative, but the cases where it's negative, it's are really singular, so we don't consider it. We don't consider this case. So what happens to the classical capacity? Does a cosmological expansion increase or decrease the communication capabilities of two quantum antennas, let's say? The answer is depends entirely on the coupling between the curvature and the scalar field. In particular, if the coupling is less than the conformal one, we will have an increasing of the classical capacity and a decreasing otherwise. This is due basically to the fact that if we put a cosmological expanding background in Klein-Gordon equation, a massless scalar field turns on to have an effective mass time dependent related to the curvature. So if the coupling is greater than the conformal one, we will have a positive effective mass, which of course will create a resistance to the inertia of these particles, and so the communication is less. On the contrary, if the coupling is less than 1/6, we will have a sort of a tachyonic mass. So an imaginary mass, the particles will have a tachyonic behavior that increases the capabilities. Okay, that was it for the results of the paper. Now I want to do a next step. Now I want to consider an expansion prior to the communication protocol. In particular, instead of considering the modes as approximately Minkowskian here, I want to consider them to be approximately Minkowskian here. And what happens? It happens basically that the factor f that I explained to you before will change. So this means that the classical capacity of this protocol is actually sensible to any expansion that happened before the start of the protocol. So basically, we can also use this protocol to test the value of the coupling, for example, or even to study the history of our universe in some way. Now, I want to study also another thing. What if instead of the vacuum as initial state of the field, we have a bath of particles? In particular, I would like to talk about a particular kind of particle, such as the cosmological expansion-produced particles. We know we all know that the cosmological expansion creates particles by cosmological particle production, and those particles are each one of these particles is perfectly entangled with the one with opposite momentum. We also know that for high enough energies, the bath is always thermal. So, okay, let's answer the question. What happens? Well, it happens that the same point correlation function will always increase. And since it's in the denominator, we have that the presence of cosmological produced particles always create a noise on the channel. Okay, we studied these two situations, and now I want to compare them. Namely, I want to compare this situation where there are no particles at the start, and this where there is no prior expansion, but there is a thermal bath of particles. We know that both those effects modify the classical capacity. If we study the modification of this classical capacity and we compare how this modification affects the classical capacity of the protocol in both scenarios, basically we can find sort of an effective particle production from here to here, because we can infer that the noise created by this prior expansion is basically the same noise given by the presence of particles. And this is a completely new thing, because in the standard Bogoliubov coefficient approach, we need 2 points where the space-time is adiabatic or approximately Minkowskian, when the protocol starts and when the protocol ends. In this way, we just need 1 point like that. So this could be a generalization of what we already know with the Bogoliubov coefficient approach. So let's put some numbers on it. A prior expansion, first of all, a prior expansion creates noise just if the coupling is less than 1/2, so we have to restrict to this kind of case. And if we infer a thermal particle production from here to here, we will have that the temperature of this thermal bath is related to this one, which depends only on the cosmological expansion from here to here and to other parameter of the detectors. So, to conclude, this communication protocol is sensible to prior expansion. And as I said before, we can use that to test the value of the coupling constant. between the curvature and the scar field. Moreover, even to study the history of a universe, because we know that it's sensible from it. In particular, we are able even to infer a particle production by studying the decreasing of the capacity in case of a prior expansion and compared to the decrease of the capacity given by the presence of cosmological produced particles. And that's it. I thank you very much for your attention, and I thank the organizing committee, the scientific one, to give me this opportunity.
Thank you, Alessio. So I will start with something. So next speaker, for example, Mr. Custer. So maybe we'll ask, I didn't understand if you can distinguish the change in the communication capacity from the particle creation from the vacuum as opposed to just a thermal bath to like end. Did you consider that difference?
Well, let's say that the difference in that case will be on the entanglement, because cosmological produced particles have this peculiarity of the entanglement from the particle with one momentum to another. Unfortunately, oh, okay, I disconnected it. Sorry. I'm sorry. Let's. Okay. Is it working? Okay, yeah. Yeah, but it's out of phase. Okay. Okay, here we are. The fact is that in the pre-last line there is a phase factor which depends basically on how on the timing where we decide both Alice and Bob to interact with the field. So let's say that there could be an increasing with respect to the expected value or a decreasing. But since it depends on the time, I have to figure it out what it means. But I just suppose that it's a sort of a unitary evolution. So that doesn't affect at all it, because it's oscillating and too much dependent on time. So the answer is, in my opinion, I cannot distinguish the two contributions, in my opinion.
Let's change in case we're ready when we're
For me? Okay, sorry. Oh, yeah, the one. How it's independent of what, sorry?
staying.
The commutator is the same, but the anti-commutator is not. No, the one on the denominator is not changing. I agree that the commutator, the one in the numerator, is not changing, but the denominator does, because of the presence of particles. Thank you. Yeah, yeah. Fabulous.
Okay. If there's no further question, we can move to the next. With Gundhi. And we talk about measuring the coherence due to quantum vacuum fluctuation. And I'm going to give you 5 minutes and 3 minutes for the total end. So if you want question time, we should finish around 3.
Okay. So thanks, Fabio. So the talk is based on an article that I wrote with Henrik Ulbrich. And in this talk, I would present a concrete theoretical scenario in which one can, in principle, measure decoherence due to fundamentally unavoidable vacuum fluctuations and discuss the experimental feasibility of such a proposal. And in the first half of the talk, I would also like to emphasize why, in general situations, it is quite difficult to measure this decoherence effect. So probably we all know, and we saw some talks in the morning, that already from classical mechanics, we know that physically fields in Fourier space can be described as a collection of harmonic oscillators. So here I have Maxwell's equation in Fourier space. Instead of working with electric and magnetic fields, I can define these function alpha, which is a linear combination of those, in terms of which the Hamiltonian can be written in this suggestive form, which is A star, A star, A. Of course, the difference when the main difference which arises when you quantize is that you're not allowed to remain at the bottom of this harmonic oscillator in the Fourier space. So if we were to be able to settle in the bottom, you would violate uncertainty principle because your position and velocity would both simultaneously be zero. And this essentially tells you that fundamentally different from the classical vacuum, the quantum vacuum has energy. So even in the absence of photons, the electromagnetic field would have certain amount of energy. And one typical manifestation of this energy, which has been measured now, is the well-known Casimir effect, which was also described in the talks of the morning. So now the question which I want to pose is the following. So we know that the quantum vacuum, unlike the classical vacuum, has energy, has non-trivial dynamical consequences. So can this quantum vacuum also lead to measurable decoherence effect if I prepare a charged particle in a superposition? So to describe decoherence, we need the reduced density matrix. So the picture which I have in mind is a particle which is in a superposition x and x prime, and its wave function is described by this symbol epsilon s, psi s, sorry. And so what we consider is the full system environment wave function, which is in the top line described on the right hand side of the equality. And to obtain the reduced density matrix, we trace over the basis states of the environment. And you see towards the end, you get the off-diagonal elements of this reduced density matrix. The suppression of the off-diagonal elements of the system wave function is given by a simple inner product between the state of the environment, which is described by this curly E. So what this expression tells us is that if the state of the environment is sensitive to the system position x, and if this overlap between the environmental state is zero, then the reduced density matrix, the off-diagonal elements would be suppressed. So what is sufficient, so what quantitatively one can study to measure decoherence is the overlap between the environmental states corresponding to two different system positions. So the lesser is the overlap, the more is the separation of the off-diagonal elements, the more distinctly the environment measures the system, and more would be the decoherence effect. So to quantify decoherence due to vacuum fluctuations, what I will calculate now is the overlap between the ground state of the electromagnetic field in the presence of interactions with the charged particle. So we have to be careful to distinguish between the interacting vacuum and the bare vacuum, which is well known from QFT. So to make sure that we are talking about the interacting vacuum, what we will do, so first of all, we know that the interaction in non-relativistic quantum electrodynamics is simply given by the position of the charged particles times the electric field of the electromagnetic field. So to compute the state of the environment, what I will do is I will start from the bare vacuum, and I will adiabatically switch on the charge, or let's say the interaction of the particle. In doing so, I will exploit the adiabatic theorem, because it is known that if the perturbation or the interaction is switched on adiabatically, one goes from the ground state of the initial Hamiltonian, which is the bare vacuum, to the ground state of the interacting dynamics. So okay, so this is it. And then in the presence of conducting plates, we know there is a complicated expression of the electromagnetic field operator, sorry, the electric field operator. What is only important to know is that it is a linear combination of creation and annihilation operators. Since pi is linear in creation and annihilation operator, two leading order in interaction, the state of the interacting vacuum can be viewed as a coherent state, and the inner product or the decoherence kernel can then be computed using standard formulas. And we know, and so what we see here is that when we analyze the off-diagonal elements, they are suppressed by this exponential that is given here. Now, at this stage, it is quite tempting to conclude that indeed there is decoherence due to vacuum fluctuations, but this is a false claim, because when the question is about whether or not there will be suppression of the fringe visibility in an interference experiment of the type of a double slit experiment, what one has in mind is a picture where in the Feynman path integral language, you arrive at the screen while being in a superposition of two paths. So you see at the point y on the screen, for both of the paths, up and down, u and l, you arrive at the same position at the screen Y. If I go back, if x is equals to x prime, you see that the overlap between the environmental states goes to 1 and there is no decoherence. So the decoherence effect in typical situations by vacuum fluctuations, as mathematically described in the previous slide, is analogous to the false decoherence effects which is there in textbooks regarding the Coulomb field of the electron itself. So again, if I consider two closed paths, P1 and P2, you see at somewhere in between the paths when x is not equal to x prime, you would imagine that since the Coulomb field of the electron along two different paths is different in its spatial configuration, you would have concluded that there is decoherence due to the Coulomb field of the electron itself. But we know this is not the case because we can measure interference fringes for an electron. And similarly, like the vacuum fluctuations, the Coulomb field is only sensitive to the final position of the electron. It is not able to measure the which path information of the charged particle. And this is what is essential for decoherence to be measured. Again, in an oversimplified way of speaking, if the environment is only sensitive to my latest position, it will not remember which of the two slits the electron passed through, and therefore it will not suppress interference pattern. Okay, so this is where the general difficulty lies with measuring decoherence due to vacuum fluctuations. It essentially sticks to the final position of the electron in typical situations, and it is not able to acquire which path information. But there is a fundamental difference between the environment of vacuum fluctuations and that of static Coulomb field, is that Coulomb field is, as I said, static, whereas vacuum fluctuation environment is dynamical. So if in a hypothetical situation I were to switch off the electric charge suddenly, it will take a certain amount of time for this information to be propagated to vacuum fluctuations or for the state of the vacuum to adjust to this new scenario. And so this is what this is essential to sort of measure the decoherence effect due to vacuum fluctuations. What the proposal that we will suggest is somehow to be able to switch on and off the interaction of the charged particle or a polarizable particle with vacuum fluctuations to exploit this dynamical nature of vacuum fluctuations and then ultimately measure suppression of fringe contrast. So of course, this proposal would be difficult to realize with fundamental particles. Because as we know, you cannot just switch on and off the charge of an electron. But what you can do is to work with polarizable particles. So this is an example shown here. So imagine that we have a metallic sphere in a spatial superposition between the plates. And if I charge the plates up suddenly, the spatial superposition of the metallic sphere would lead to a spatial superposition of dipole. And in doing so, I have switched on the interaction of the otherwise neutral particle with the electromagnetic field, because when the dipole moment was absent, the particle was not interacting with electromagnetic field. However, in this setup, you would need to switch on and off you would need to charge the plate suddenly. And this is limited by the speed of electronics, and for all practical purposes cannot be done fast enough. So the reason why it cannot be done fast enough is because you have to compete with the speed of light. So if we consider a typical plate separation, which is of the order of centimeters, the time scale of the environment is L over C, which is less than a nanosecond. So to be able to physically switch on and off the charge, you need to be able to charge the plates faster than a nanosecond, which is physically not feasible with current technology. So in the end, what we ended up proposing is a Talbot-Low matter wave setting. So essentially what happens is that instead of having a charged plate, what we do is to switch on the dipole moment of particles as it passes through a laser grating. So we see that as the particle approaches the laser grating due to the interaction with the light, there is a dipole moment of the particle which switches on. And as it exits the laser grating on the other side, its dipole moment is switched off, which is again a mechanism which we need to sort of disrupt the nature of vacuum fluctuations and not to allow them settle to the particle location completely. So again, what would happen here is, since the laser has a spatial profile, there can for a certain position x, you can have a finite electric field of the laser for which there would be a finite dipole moment generated, while on some other x prime, the dipole moment can be weak or zero due to the spatial profile of the laser. So what you imagine is what would happen in this superposition x and x prime is that essentially the vacuum for the branch X goes into the interacting vacuum, while for the branch X prime, it remains in the bare vacuum if the electric field there is rather weak. So by creating a spatial superposition of the particle, you create a superposition of interacting and non-interacting vacuum state. Again, the calculation goes through as we discussed before. So you have dipole moment now, which is a function of time, which you can switch on and off. And then you calculate the overlap between the two different states. So one is the bare vacuum and one is the interacting vacuum. And you see this decoherence kernel, which is being plotted. Again, I emphasize that D equals to 1 implies that the overlap between the environmental states is perfect. So there is no decoherence. And the closer D is to 0, the more is the decoherence effect. And this formula essentially is now strongly dependent on the parameter alpha, which essentially depends on the amount of dipole moment that can be generated for the molecule. So the physical conditions that are required are essentially that we want to be on the green curve rather than the blue curve, because for the blue curve, we cannot measure decoherence. And on the green curve, by just inverting the formula, we see that you need to be able to generate a dipole moment, which is of the order of 10 raised to minus 22 coulomb meters. So now the question becomes, can we physically generate, are there molecules for which this dipole moment can be generated? So we directly start with sodium clusters, which are with current technology the largest molecules for which matter wave interferometry is performed. They have a mass of about 10 raised to 6 AMU, which means that there are 10 raised to 6 protons and electrons in this big sodium cluster. So if you do a standard calculation, you see that the total charge that can be displaced is about 10 raised to minus 3 coulomb. The particle typically has a size of nanometer. So charge time distance gives you the dipole moment, which is 10 raised to minus 22 coulomb meters. This we see does fall in the range that we need to be able to measure observable decoherence. Then the question becomes, can you generate this electric field in experiments, which is able to separate the positive cloud and the negative cloud of the molecule to its diametrically opposite ends? And the answer is yes. So to summarize, essentially, the conclusion of the analysis was that not only on paper you can have a decoherence effect due to vacuum fluctuations, but there exist molecules, for example, sodium clusters on the mass range of 10 raised to 6, a million atomic mass units, for which people are beginning to perform matter wave interferometry. And so in principle, this decoherence effect can be detected in the near future. Okay, thanks.
Thank you both for the next talk. Questions?
Yeah. You mean the falls? So, I mean, the falls come in, it's a bit more technical. So when you compute the 2-point correlation of the vacuum state, there is a divergence which comes due to infinite image charges that you have. But for all practical purposes, you will not be able to measure these sharp falls in an experiment, because let's say the time which is denoted here is the time for which the molecule remains within the laser grating, and you would need a very high precision control over that time to be able to measure this decoherence, these dips essentially. So theoretically, they come from the periodic nature of the setup that I have. So you have infinite image charges, and they sort of have this divergence in the 2-point correlation, which comes here in the periods of L over C. Yeah, so what you would try to measure is basically the flat line, and maybe in a smarter way you can also measure the sharp peaks. But for now, at least what you can measure is the flat. Okay.
Okay, let's thank the speaker again. While we set up, our next speaker is Alex Matzkin. and it's not what we have on paper. The title is Wave Packet Tunneling is Causal, Relativistic QFT Approach.
It's not on the program. Okay.
There was the wrong part of the program. But anyway, I'm going to give you a sign of 5 minutes and 3 minutes from the end,
Okay.
including the questions.
Fine. Okay, thank you. Okay, so yeah, so my talk is about the tunneling time debate from a QFT viewpoint. So this is done in collaboration with Mohamed Al-Khatib, who is now in Namur. At the time we started working on this, he was working on a PhD with me. And he will give a talk tomorrow on the same approach applied to curved spacetimes, so tomorrow afternoon, I think. And it was also done in collaboration with a Bilbao group, Javier Gutierrez, Marisa Pons, and Dmitry Sokolovsky. So just a refresh on what the tunneling time debate is. So remember, you have an initial wave packet here, an initial particle, which is a wave packet, a potential barrier, you launch the particle. And what happens is that 99.9999% of the wave packet is reflected, but a very small bit is transmitted. And this is the purple wave packet that you see here. It's very, very small, but the debate is that if you just let the same wave packet evolve without a barrier, so it's a free wave packet, it's here, it would be the green one. And as you see, the purple one is advanced, so seems to go faster relative to the green one. So that's the tunneling time debate. And remember that it's very small, so actually it sits within the tail of the green one. Purple one is within the tail of the green one. So if we want to determine what is the tunneling time and confirm whether it can be superluminal, well, we have the following problem, is that there is no way, not in any ambiguous way, because there's not one tunneling time, but many candidates. Because, as you know, there is no time operator, so we don't have any time eigenvalues. Again, remember that the properties in terms of quantum mechanics rely on the eigenstate eigenvalue link, so this is not going to help. If you want to compute the traversal times, then you're going to disturb the system. Then arrival times, again, are going to be a problem because you have a fixed position and you're going to collapse, let's say, to that position, but this will involve different times and so on, especially the expectation values, for example. You're actually going to have a conditional expectation value if you just take the expectation value of the transmitted wave packet. So there's no way you can unambiguously determine what tunneling time is in quantum mechanics, and this is, of course, why it's interesting and why you have the debate. So on the experimental side, well, on the theoretical side first, you have different time. You can propose different time definitions, but basically you have phase times related to delays. Look at the phase. You can also have the weak values as like following the particle inside the barriers. This is the main idea. And on the experimental side, you have many experiments, but time-resolved experiments are difficult. And they often rely on the theory because you have a lot of parameters that are model dependent. Nevertheless, especially if you look at all the papers that were published, most of the papers published in the last 5-6 years, you see that all of them claim that experimental work, I mean, tunneling time is superluminal. So most of these work come from attosecond experiments in which an electron goes through an electric field barrier, except this one is the opposite. It's a photon going through an atomic barrier. But they all claim that tunneling is instantaneous, superluminal, so negative time, by well adjusting their observations to some models. So as you know, Schrödinger, if your model is based on the Schrödinger equation can account for superluminal times because there's no velocity bound, so velocities are unbounded, so that's not going to be surprising, let's say. If you go to relativistic quantum mechanics, for example, the Klein-Gordon or the Dirac equations, you know the propagator is causal, and the velocities are bounded by the velocity of light, of course. Nevertheless, you have many authors that defined operators, time operators, using a relativistic framework, and they conclude that it can be superluminal. So here you have a time of arrival operator that is superluminal. In this case, you have a phase time that is superluminal. Here it's about doing the expectation value of the transmitted wave packet. It's also superluminal, and so on. So our goal in this work was to use relativistic QFT because we have this property of microcausality, and we know what microcausality is. And what we tried to do, so its definition is here, right? That if you have two observables that apply to space-like separated events, they should commute. And so we tried to link microcausality to the wave packet dynamics. So to do that, we need a form of QFT in which we can compute the space-time resolved solutions dynamics. And this is what we have done. So it's pretty, the QFT we use is pretty standard. You have the field operator, so here you're written for the Dirac field. The only, let's say, specific aspect is the Bogoliubov transformation you see here that gives you the field operator at some time t as a function of the initial field operator. And this is what allows us to compute the time resolved, space-time resolved dynamics of the wave packet. So just let me tell you that in order to do this, we also need to write the initial wave packet that you see here as the QFT state. As you know, this is related to the first quantized version of the wave packet amplitude. And we have done this. So the electron is a Dirac field, but the barrier is a classical background field. So that's another approximation we are using. We are using a background field, which makes actually the problem easy to solve. Otherwise, it would be a lot more difficult. So just to give you a glimpse of what the formalism gives you. So just giving an example here for the electron density, not the charge density, just the positive frequencies associated to the Dirac field. So this is just to give you the field operator as it's developed in time. We're not interested in the detail, just try to understand what we can obtain with this. So the QFT state, the initial one is the same because we assume we have an initial electron. And just so I didn't specify here. So if you want to compute the density, it's of course the expectation value of the density operator with chi, which is the initial wave packet, right? Which is the same as I just said. So forget about the details. The only thing important in this slide is that the full density for the electron can be parsed into two bits. One which is the density due to pair creation, because if you have a barrier, you will create particle-antiparticle pairs. Even if it's exponentially small for a low barrier. And then the other bit is the wave packet density. And these things, you can follow them in space-time. And this is what I can show you here without, again, getting to the details. The black line you see here is the full density. And the dotted one is just the part belonging to the wave packet. So never mind. So here is the case, but here you see it's a very narrow potential barrier. And here it's coming towards the barrier. So this is the particles that were created by the barrier. And here you see that a huge part is transmitted because this is Klein tunneling. It's not standard tunneling. But this is what this gives you. You can really follow the evolution in space-time. Let me just remind you that if you start with a pure electron, as you know, you cannot compactly localize initial electron, which means the wave packet must have tails. So if you're unhappy about that, we kind of try to do something, and something means to come up with a formulation that would allow for initial wave packets with compact support, but then people, pure QFT people will be unhappy because you can't properly define a quantum field theory in that way. So this is important because I'm going to use this thing to show you introduce the proof, not really to prove anything, but here's the main idea. You start with your initial wave packet, and which is here. It has infinite tails, but we don't care because we define a region in blue in which we will do an intervention. An intervention means we will change the wave packet, the shape of the wave packet, for example, without, of course, changing the total charge. And then the question we are asking is, okay, let's look at some time delta t later. So if you look at the light cone emanating from the right edge of this blue region, it would be here. So this region in purple is causally disconnected. It's outside the light cone. And what we can show is, by using a microcausality, that if I make an intervention in this blue region, D, then this intervention has absolutely no effect in this causally disconnected region. Meaning that the process has to be causal, because otherwise, if you change the initial wave packet, you would expect, if it's superluminal, to see something happening in this purple region. So how do we do this? Okay, we start from the definition of microcausality that I just recalled. In the free case, the proof of microcausality, you can look at this in any QFT textbook. If you include a background field, you can look at the proof in one of our papers. And then we have this intervention d at t equals 0, followed by the measurement of the density in this causally disconnected region. And this can be written as a correlation function, which is this thing. So it's the expectation value of this mutilation operator, because we kind of changed the initial wave packet violently by changing its shape. And then the observation of the density will take O prime to be the density in this spatially disconnected region. And it's fairly easy to show that this correlation function does not depend in any way of the operation you have performed initially in this blue region. And this holds provided, of course, microcausality holds. So there is a two-way implication here. This would be the conclusion. The take-home message is that the dynamics, I mean, you can define superluminal times if you want, with a phase, with amplitudes, whatever, but the dynamics has to remain causal. Otherwise, you have a problem with microcausality, and this is something that doesn't look very, very realistic. And before finishing, I would like to advertise this poster, which will be presented by Florent Daen, who is currently doing his PhD with me. So this is a poster about the Newton-Wigner position operator. And basically, he will prove that the Newton-Wigner position operator cannot be taken as a real physical thing, because otherwise you can, using super radiance, you can become superluminal arbitrarily in any arbitrary way. You can have amplitudes propagating faster than light. And this is a poster about some recent results we just obtained on the Newton-Wigner position operator in the form of a full Gaussian representation. Thank you very much.
Thank you for the talk. So how do you model interventions in this context?
So the intervention is simply we have an operation that redefines the shape of the wave packet. For example, instead of having a nice Gaussian, we have something that has a wiggle. So actually, technically we impose a sign to some power function, such as the total charge is conserved. So it has a different shape inside D, but the tails remain the same outside the blue region we showed.
So it's a choice of initial state.
Yes.
Any more questions? Time to the next speaker. Now. So let's thank the speaker again. And our next speaker is the topic is the RQI North.
Okay.
Start is 1:20. Because that one phenomenon. So quantum entanglement among axions, photons, and gravitons inflation. And so I will give you signs 5 minutes and 3 minutes before the complete end. So if you want question, you should finish around 3 minutes.
Okay, thank you. Today I will talk about quantum entanglement among action, photons, and graviton from inflation. So the collaborators are as follows: Taiki Ikeda and Yuka Kaku. She's and Tsugumi Kando. So let me start with the following belief. I believe the gravity is quantized. So if so, the graviton exists. So, and if string theory is correct in the sense that the string theory can explain the actual our nature, then in that case, action exists. So we would like to detect action and graviton. To this end, we study action photon and graviton conversion. Let me explain it a little bit. For example, if you take a look at the action of the action interacting with the electromagnetic field, you have this kind of the interaction term. A is action field. Then in the presence of the background magnetic field, this action field A interact with the electromagnetic field. So because of that, action can convert into the photon or the vice versa. And similarly, in case of the graviton can interact with the electromagnetic field through the conventional minimal coupling. So the graviton can convert into the action photon, and photon can convert into the graviton. So in this talk, I'll show two key results. This conversion probability is enhanced by the squeezing from inflation. And the next one is the entanglement is generated by this conversion process. So I hope it opens up a new avenue for the graviton search. So let me focus on the action photon conversion. Action can be detected through those two experiments. First one is the helioscope experiment. There exists, people believe that there exists solar action. So to detect the solar action, we have this kind of telescope. In the telescope, we have the strong magnetic field imposed. And because of the magnetic field, we have the conversion process. Then we can observe the photon, X-ray photon, by this detector. And the next one is a light shining through wall experiment. We use laser. Laser cannot go through this wall between the detectors. But if conversion occurs, action, photon can convert into the action, and action can go through the wall. Then action again convert into the photon. Then we can detect that photon. This is the basic idea. And more precisely, if we start with this action, then you have the interaction between the action and the electromagnetic field parallel to the magnetic field psi. So we have the effective two-scalar field action. So there is an interaction term between phi and psi. So the simple field theoretical calculation gives rise to this probability. And this is using this probability that experiment are conducted. So now I would like to generalize. So So in this analysis, people analyze the process using the wave dynamics. So it's essentially classical. So we cannot incorporate the quantum state into the analysis, but we can do that if we correctly consider the theoretical process. We have this interacting Hamiltonian. So the state is evolved under this Hamiltonian. Then we can consider the various quantum state. For example, squeeze state is just the eigenstate of the annihilation operator. And not squeeze, coherent state is the eigenstate of the annihilation operator. And you can also consider squeeze coherent state, which is the eigenstate of the annihilation operator constructed from the original annihilation operators using the squeezing operator. So using this quantum state, we can reconsider the conversion process. For example, we can consider the first one is action. Action is squeezed during the inflation. So squeezing parameter is huge because of the rapid expansion of the universe. And we can also consider, we can control the photon, and we can also consider the squeeze coherent state of the photon with a single photon added. So that's the initial state. Then we can consider the conversion process. Then we found the enhanced probability. So we have the enhancement by this factor e to the 2z. Z is the squeezing parameter of the action field, which this squeezing is produced during inflation. Okay. So this is a huge enhancement. Similarly, we can analyze graviton to photon conversion process. The action is a standard one. The minimal interaction produces this second line, this interaction. In the presence of the background magnetic field, we have the mixing between the metric and the electromagnetic field. So we can canonically quantize the system. Then the interaction Hamiltonian reads as follows. This plus is in case of the gravitational wave, plus mode is just this quadrupole oscillation, and cross mode is just 45 degrees of rotation of this plus mode. And cross mode in the electromagnetic field is just cross mode is parallel to the magnetic field, and plus mode is perpendicular to the magnetic field. Both polarization modes are decoupled. So we consider each polarization mode separately. Then in this case, we can also consider the graviton state, which is highly squeezed because of the inflation. And we can also consider the state of the photon with a single photon added. So the calculation is quite similar. And the result we got is as follows. So the last one is probability. You can see the enhancement factor, the same enhancement factor e to 2z and e to 2r and beta scale. Beta is a coherent parameter. Now, using this conversion process, we can do the following again. For example, let's consider the first one. You see, we have a entanglement between gamma 1, gamma 2, which is different modes of the photon. Both are entangled. But after the conversion, we get the second line. There we have the entanglement between photon and gravity. So this is nothing but the entanglement swapping. More interestingly, if we start with a separated state, there is no entanglement initially, but after the conversion, we can generate an entanglement state. So this is a kind of the quantum generation process. So in case of the classical process, this never happened. That's why we believe that this will be a hint that gravity is contained if this process can be detected. Okay, so let me summarize my talk. So you can read. But I repeated the same thing. Thank you very much.
Hey, thank you for that very nice talk. We have time for a few questions. I can start one regarding your last point. So you mentioned that at the end that the effect will be a hint in the composition of the property. Now I'm interested how would you draw that conclusion? I had the impression that the whole calculation was all within quantum field theory, right? There is no comparison to a theory where gravity is not quantized. So how would you conclude that this is a hint of the quantization of gravity and not perhaps an effect that can also be explained by a classical theory of gravity?
Mm-hmm. Okay, that's a good point. If you want to compare the something other, for example, you can consider classical and quantum gravity. Recently, OpenHAM, they propose a theory. So at least we can compare both OpenHAM theory and standard conventional quantum gravity result. Then we can conclude which one is correct. Get it? No. This is a minimal coupling. No. We are considering minimal theory. So the squeeze state is produced only in the gravity state, not photon.
People think about the questions. Next speaker. Maybe one last question from me. Maybe yeah, maybe you can change laptops in the meantime. A little bit of follow-up, last question maybe. How much is your prediction model dependent? Like, of course, it presumes the existence of axions, but how much the entire interaction between axion and gravitons is model dependent, robust would be the prediction?
So we have considered the minimal interaction between photon and graviton, and standard. I think this is a unique action between the action and the photon. Chance-Simon coupling. This is a unique action. So only the ambiguity exists in the magnitude of the coupling. So maybe we can constrain the magnitude coupling, and if the action of the graviton is quantized or not. So there is some contamination between this. Yeah.
Okay, thank you.
Thank you.
Currently, sure. My email wasn't received with organizing status, so maybe one more question. Okay.
You can take that.
We can thank the speaker and so, as it was mentioned in the panel, I want to remind everyone that every day, everyone goes in the positive should sign the credits because funding is critically dependent. So how much money the local organization gets depends on those signatures being there. So please every day check the rest of time, the constraint. If you're not part of the construction, and especially so far the European Union, not avoiding invited to SNAP. Really, it doesn't get any commitment. You can do it, and you can silence the emails at some point. But as soon as he sends himself as email. The email that I sent wasn't received by the organizers, so they don't have the slides. They don't have the slides yet. But it's like, I just downloaded them and I just sent it on their email, so now they can. Oh no, I have an Linux computer that are running. In a minute. So just the field out. So we have a centric Perche as our last speaker. The slides are coming up, and with them will be the last speaker title, which is how much record value is there between two finite space-time rings? Yes. Perfect. Thanks you so much, Fabio. Welcome everyone. And let me start by thanking Gaetano for this this organization and for allowing me to speak. Also, let me clarify, I'm not a member of the local organizing committee, contrary to what Gaetano stated earlier today. So today I'll talk about, well, I'll try to give some hints towards how to answer this question, right? If you fix two causal diamonds to finite space-time regions that are causally convex, in space-time, how much vacuum entanglement is there between these two? That's the question I'm going to try to address. But this is a hard question to be addressed because, but before actually addressing it, let me just
start with a disclaimer that was kind of mentioned or hinted at in Chris Filster's and Doreen's talk earlier this morning, which is that these local degrees of freedom of quantum field theory, they live in these algebras of observables. And in the simplest cases, these algebras can be built from these smeared field operators. So basically, you consider completely supported functions that live within these space-time regions, and then you smear your quantum field within these, and you get your basic observables that can be used to build this algebra, this local algebra of observables. So these are the local degrees of freedom, right? Now, if we want to quantify entanglement between these local degrees of freedom, it's very hard for two main reasons. One is that we don't have just a tensor product decomposition between degrees of freedom here and there. It's not an HA tensor HB. So we don't have this tensor product composition where usually entanglement is phrased. And then, of course, to each finite region of spacetime, there are infinitely many degrees of freedom that are associated with the quantum field in each one of these regions. So we're in this case of no tensor product decomposition and infinitely many degrees of freedom. Our only hint is the fact that space-like separated observables commute. So what do we know about entanglements in quantum field theory? Let's start with a simpler case, which is entanglement between complementary regions. So entanglement between one causal diamond and everything else. So in this case, because the vacuum is a pure state in the whole Cauchy surface, if you will, or in the whole space, then the entanglement entropy is an entanglement quantifier. And if you compute the entanglement entropy there, introducing a small UV cutoff, epsilon, you see that this entanglement entropy is divergent as epsilon goes to 0. This means that there's an infinite amount of entanglement between any finite region and its complement. Also, there's this more recent reference here, the 5 here, which actually shows that you can extract any arbitrarily entangled state from a region's complement by allowing yourself to consider arbitrary couplings. Now, when you consider two non-complementary regions, this really changes, because now the reduced state to these two regions is a highly mixed state, right? It's not a pure state for sure if you only look at the state at OA and OB. So in particular, entanglement entropy would not be an entanglement quantifier here, and we have to figure out other ways of talking about entanglement between two finite-sized regions. So one of these ways is entanglement harvesting, where one considers probes that couple to the field into space-like separated regions. The space-like separation ensures that the degrees of freedom that each probe couples to are independent field degrees of freedom. So if you are able to extract entanglement to the probes, this would signify that there was entanglement between the regions where the probes couple to, because these are independent degrees of freedom. And this is important for two reasons, or relevant for two reasons. One, from a fundamental perspective, to quantify, to attempt to witness the existence of vacuum entanglement, but also from a practical perspective, if we could really extract a meaningful amount of entanglement from the vacuum, then, I mean, this could potentially have uses in quantum computing and in other practical applications, right? So usually a typical setup of entanglement harvesting will couple like a qubit or something. So this would be the dynamics of the qubit. There's a sigma x operator evolving on time, and then it will be coupled to the field along this interaction region, which is this ideally compactly supported function lambda x in spacetime, which defines where the qubit couples the field. Then this small coupling constant, so that we can use perturbation theory. Great. From this, this very simple model is the underorbit detector. It can reproduce numerous physical systems, superconducting qubits, atoms, things like this. So the typical setup goes as fixed two regions. Now, pick your probes, maybe atoms, maybe superconducting qubits. Now you're going to couple them for finite times to the field. into spacely separated regions to ensure that the field degrees of freedom are independent. Then you find parameters of these probes that would allow them to extract entanglements. And a typical plot of entanglement harvesting looks like this. Look at the blue curve, which is the negativity, which is an entanglement quantifier for the qubits. And then what happens here is I'm varying here the energy gap. I'm seeing that if the energy gap between the two levels is too small, there's no entanglement, then it peaks at some point and decays. Now you might notice here that we have a negativity of 5 times 10 to the minus 6 times perturbative parameter squared. That's very small. That's a very, very small negativity, right? So why is it so small? Is there any way of like increasing this, of enhancing this protocol? Or what are we missing here? So another approach to this, which I'm calling the Gaussian approach, is the following. So you can represent the local degrees of freedom of a quantum field in terms of this infinite dimensional algebra of observables, but you can always find some modes or some field observables, if you will, that satisfy the canonical commutation relations. And thus, you can associate these degrees of freedom associated to these observables to basically a classical phase space, where you would talk about the field degrees of freedom or at a given state in terms of its Wigner function. And if you do this, basically, all the degrees of freedom associated to a given state are encoded in these expected values of anti-commutators of these smeared field observables, at least up to the cutoff of the observables that you considered. So basically, we only need to compute this, and we can potentially access arbitrary information about the field or about this given state of the field. Cool. So another way of doing this also is, instead of looking at these four smeared, covariantly smeared field observables, you can fix a Cauchy slice and talk about the smeared field at the slice and smeared momentum at the slice, kind of corresponding to initial conditions of your field. There's a correspondence there. And then it turns out that you can represent the four smeared fields as a combination of the three smeared fields and so fields and momentum here. There's a specific way of doing this, but this simplifies some of the description. Okay, so how do we quantify entanglement using this Gaussian formalism? What we do is consider many functions, Fia and Fj, Fib, into regions A and B, compute the expected values of the anti-commutators of the field with itself and the momentum with itself in the vacuum, put them into this covariance matrix. You don't have to compute the cross terms in the vacuum. And then you can compute the logarithmic negativity between these two regions by basically computing these symplectic eigenvalues of the partial transpose covariance matrix, right? So basically, this is in principle simple computation to be done if you have the covariance matrix sigma, right? If you have sigma, compute some eigenvalues, you get your negativity, which is a quantifier of distillable entanglements in this case. But there's more than this, because Natalie Kelko, in this paper here and a series of other papers, she actually showed this method for separating the modes that individually contribute to the negativity. So the idea is, if this is the set of all of your modes in A and B, there's this symplectic transformation corresponding to a unitary transformation in Hilbert space, such that, or in the algebra, or the equivalent of that, such that basically you separate each pair of modes that individually contribute to the eigenvalues that contribute to the negativity. So in particular, you can find the most entangled modes between two regions by building this symplectic transformations. And for instance, this is what Natalie has in this paper here. This is for 1D and 2D. Here you see like two regions separated by 1.88. One is the size of the regions. These are the shapes of the momentum profile modes. And below is for 2 plus 1D. So she does this using a lattice theory approximation, but basically the method works in general whenever you have these covariance matrix descriptions for your state. So what's my goal here? I want to pick a real basis of L2 normalized functions for a given region and another region. And then in that case, the commutative relations will automatically be satisfied between the smeared field and momentum operators. Then introduce a cutoff for this, consider as many modes as feasible, and then find the most entangled modes between these two regions by using this idea. And then once you singled out these modes, you apply a mode swap operation, you extract entanglement that is present between the most entangled modes between two regions. So more concretely, what my computer is currently running, not these computers, but another one, what I'm considering is two spheres, right, in 3 plus 1. Then I'm picking the eigenbasis of, the eigenfunctions of the Laplacian with Dirichlet boundary conditions on the sphere. And then this is basically a plot of the logarithmic negativity as a function of the number of modes considered, right? This 0.2, this is much more than 10 to the minus 6 times lambda squared, right? So there's way more entanglement than random detectors can extract. But also, this is the approximate shape for now, with the current cutoff, of the most entangled modes between these two regions. So this is what I'm currently working on. I don't have any concrete results. This is still running, but hopefully this will be out soon. But I guess the summary, the conclusions are that our current methods to talk about vacuum entanglement extraction are very unoptimized nowadays. And recent developments allow us to find these most entangled modes. So to potentially measure this and really get meaningful values for the entanglement between two regions or two probes, we should couple to the most entangled modes and extract that entanglement from them. And of course, this could increase the entanglement extraction to significant values. So thank you so much. Questions, I guess? Questions? To the questions. This one, yeah. That's a great question. So I'd expect entanglement to be finite for any two regions that have a finite separation between them. But I'd expect this convergence to be logarithmic. So it will take a while for this plot to really asymptote to a flat line. Can we talk about this during the coffee break, maybe? There are lots of like, yeah, it's a great question, but it's yeah. Forever. You think that the entanglement between two finite regions is infinite? The entanglement, not the mutual information, not anything like this. The entanglement. But the mutual information is bounded, like it's finite. If the mutual information is finite, the equivalent must be finite. Okay. I'm sorry? Sorry, wait, which one? Yeah. That's what you get from the decomposition. Yeah. I agree, and I was also very surprised when I studied basically this decomposition here, and it gives to you the phi and the pi alone by themselves. So it's like that's what you get in the end, and this does give you the most entangled modes if all degrees of freedom are really being considered in your covariance matrix, which is not the case here, right? Because an infinite dimensional thing. Yeah. No, but if this works in the lattice, why wouldn't it work here? Right? That's my yeah. Hmm?
Okay. Think that if you have any one question,
Sure.
follows. Okay. Okay.
Can you? Sure. Yeah. Now I have to talk to people. Yeah. But you're a monk. The mutual information is finite within 50 years with finite separation. How do you know? Oh, because I looked at some ADS CFT calculations. Sorry, CFT calculations. They compute it, it's finite. It's finite, and it decays with the separation squared, the mutual information. It's basically proportional to the product of the radius of the spheres divided by their separation squares in 3+1. So if the mutual information is finite, then the entanglement must be finite, right? If you have one region that complement 100%, but these are two finite regions.
has 15 minutes, including questions. For if you want to have time for questions.
It doesn't seem that that's working either.
And next speaker come down while the previous one is taking.
Okay, that makes me feel much better.
Like if we prove that these things will be faster, even if you
If
see on your computer.
even his isn't working.
Okay, so let's or buy your own projector. I don't know what else to say.
Yeah, that saved me the worry when it didn't work on his computer.
Okay.
I was like, okay, it's not my fault. Oh, in 15 minutes, that would be a mission. Yeah, and it was working fine. Just
Everyone, yeah.
yeah, the whole session before was perfect.
Yeah.
Oh wait, is that loose?
It's like it's not seen and
Yeah. I just checked that, but I don't know if these are even connected. Maybe they are.
Okay, so the neutrons go in front of now. Ask how much do I pay? The driver said, no, there's no charge for me.
I think we have to call a technician. I don't know what to do on it. I think we have
I know even less than this. I
I
really know the technician.
think we're
Yeah, but there is a lot of time.
So what's is there any? But so now nothing is working.
no, nothing is showing up apparently. Sorry? We've tried two computers. Nothing is even, it's not even realizing that it's plugged in. It's not it's not my computer. It shouldn't be Alessio's. He's used his already.
That's stupid. But did you try turning off and on the beamer if it's possible?
You want to have mine for not.
Yeah,
Yeah, if we can figure out where that plugs into over here, maybe. I guess we give it a shot, right? Would maybe into here? Don't worry, this isn't stressing me out. Yeah, do we plug the other one back in now and then push a bunch of buttons until it works?
Yeah. So what is 1 and 2 and 3?
Thing in one. What about three? Nothing.
Let's put that here. This is on. This is a beamer. Let's see what is.
now you turn it off.
Now you turn it off. That's the only IT trick I know.
That's the only. It's about the only one I know too. So don't worry about it.
Well, okay, now it's not coming back on. So
Maybe just in case there's something that should be here, try just putting this one back in.
now I mean,
Oh no, I mean,
just waited.
no.
Sure. All right.
Yes, it's worth a shot. Thanks. Well, at least we'll all have a good sense of humor about it.
So so this is your postal and the ATX system. That's not and then the other meeting should be 20. That's even if everything was perfectly fine.
All right.
Don't have many copyright. I have to stay here and hold and
No, it's okay. It's okay. Yeah.
Yeah, but I mean, what impostare data e ora? No, that's so. What do you think happened?
Usually that's what happens when nothing is attached. But now
We've tried 2 computers that have been used. And I've used this computer plenty of times.
no, qua non funziona, sul proietto Haas. Michele, sì, sì, qua. Qua è il problema.
Yeah, because you've used yours already for presentations, yeah? Yeah. Okay.
Eventually fine.
Yeah. Perfect. I mean, hey, if that's the case, then something might have just gotten disconnected and none of us know where it is.
Yeah, and so now we are one talk late.
Unfortunately.
That we have I think one talk space, and then less than one talk space from the next event. And that's not going to work.
Just trying one more computer.
Now I'm gonna have to find
Oh, no, wait a second. I know, yeah, exactly that.
And just I guess just to see if this one works.
It's like I guess, together the work of the net, making sure that everything works and that data stop all the time.
You think your mere presence will scare the
No, no, no.
projector?
Let's see if it happened before, I had the time to call before the contract start.
No, it only happened because people stopped looking at it. That's how technology seems to work for me.
Hopefully, yeah, it could be easy. That's why something, yeah.
But
maybe
it's
the
locked.
keys.
So there is literally nothing we can do. Yeah, I don't know. The online powers and capabilities is annoying.
Blackboard might not be such a bad idea after all.
It's this is really old school. Like you don't even have chalk. No, there is chalk. Okay, the erasers are. If you have anything,
I mean, if that's what people would like me to do, I can try my best and give quick sketches of what I wanted to show. It's
want to give it a shot.
I guess it doesn't hurt, right?
Back online, I guess I can give you 5 more minutes at the end.
It's no big deal.
Okay, let's try.
Yeah, I'm gonna need my slides to remember, but
20. And Boris Ragula, is it?
yes, sir. Yes.
Usually I read it there. So Boris Ragula will try to do this also.
Yeah.
This is even a quite not optimized blackboard, so yeah, probably you may want to come and
No.
down for that.
What's
Sorry?
I'm happy to show them to anybody. I've got my laptop.
I don't know. Do you have any better idea?
Yeah, do you have another suggestion? I'm happy to keep waiting too.
Yeah, that's it. Okay, so we can.
I guess we can wait a second now, but
If you want to start give some. Okay, maybe let's wait a minute to see if you can.
Sure. I have no other option right now, so. Fair enough. Yeah.
Try to get it to work.
Yeah. I mean, I'm gonna try my best. I can't do it.
Sì, prima tutto a posto, sempre, non avevo dato mai problemi tutto il giorno. Adesso diciamo che vabbè. Non funziona nessun computer, abbiamo fatto in questo. Ci vuole accendere.
Beh, adesso ci metto un minuto perché ho già provato a spegnere e accendere.
No, fammi
Ci metto un minuto per tornare già. Ho provato a spegnere e accendere, cioè, sì, adesso ci vuole un minuto per riaccendersi. Però sì, abbiamo provato a schiacciare 1, 2, 3 lì. Aspetta che succede qualcosa qua.
No, no, solito, se avevi
Eh?
provato. Siccome hai provato tu, no? Hai dato di energia per la cosa. Non c'è. Non abbiamo. Così è come se proprio funzionasse, ma non leggessi nessun contenuto. Abbiamo visto, abbiamo provato con questo, non funziona, è uguale. Per leggere non ci si ah? Invece sì.
What's that?
Ma che attendono in realtà. Anche questo ci ha fatto 2 presentazioni con questo. Quando
What's that?
dopo una cosa da. I can do whatever you want, that's what I will do.
Fair
Very
enough.
strong.
Yeah, I'm just not sure. I'm just not sure if it's better of me saying, okay, I can give you all of the information, or like,
You can say, you can just write the archive reference there if you want. They say, look, what I prepare is not really doable in 15 minutes on tiny fix is true.
yeah, that is true.
To
Yeah,
the
I would have to say it's got to be longer than 15 minutes, but yeah.
telling you guys taking up.
Otherwise, I might be able to do it at a different day. I mean, it would cancel everything.
And that term does not exist in mechanics, in any mechanical system. That is alien to mechanics, right? So derivatives in space are not a property of ordinary differential equations. They have to be a property of partial differential equations. So the only derivatives that you can have in an ordinary differential equation is a derivative in time, not derivatives in time and space. And basically, if you, I often get this question that Nabla square appears in the Schrödinger equation, right? But that is not the same Nabla square, right? So this is the Schrödinger equation contains derivatives with respect to the coordinate in a configuration space, and this is the Nabla square that corresponds to coordinates in space-time. So it's not the same thing, right? So there is the Nabla square, and then there is the Nabla square thing, so to speak. So basically, this is the statement that they often represent as the statement Q is not equal to X, right? So the coordinate in the configuration space is not the same as the coordinate in space-time. Do not confuse these things. So what does this presence of this spatial coordinate term basically tell us? Well, it tells us that the initial conditions are not enough. It is not enough to specify, when you work with partial differential equations, you cannot specify purely the state of the system and the velocity of the system, like the position and the velocity of the system. You need to deal with spatial boundary conditions. And this is something that I had to often emphasize this to various people, that keep track of boundary conditions, because these things are important in field theory and they're important in gravity, of course. So that is the third thing that is not the same in mechanics versus field theory. So, okay, this is enough. I don't want to go much further into these things, but the idea is to provoke you to think about these things rather than give us any type of particular answers. So, thank you. The conclusion.
Thank you, Martin.
Thank you very much. So for your second statement, when I understood that it's still one of the sorry, it's working. It was working on the sort of it's working my impression, everything you can do isotopic reporting testing, testing that your formalism you can repeat it. So I don't know that's what exactly the difference that happens in the there. What's the deflection?
No, that's the
Yeah. Okay. So Haag's theorem is a formalization of this statement, basically. But the thing is that in principle, there is a formalism that corresponds to the Schrödinger picture of the quantum field theory. But that formalism is the so-called Schrödinger functional formalism. And I'm not sure what you read in that book, basically, if that was the one or not. But the Schrödinger functional formalism is something that is very, very rarely used, to the point that it is not being taught in school at graduate level to students. So this is very, very specific, particular thing, and quite often, for example, in gravity, due to gauge symmetry, the Hamiltonian ends up being 0. So how are you going to write down an equation, evolution equation for that? So it's it's just not a good idea. I mean, the formalism does exist, but it is overly complicated, and it is not what you expect it, not what a typical student would expect it to be, when somebody tells them about the Schrödinger-Heisenberg pictures. Yeah? That was the whole point.
Okay, thank you, Juan. Thank you.
Should be near your foot, so otherwise it doesn't feel anything. Okay, well, let's see. Maybe here.
And 3 minutes before the end, including questions. So we should try to wrap up after the 3 sign.
Okay, let's try my best. Yeah, I understand that. What's
Okay, our next speaker is Rosati.
oh, perfect.
And he will tell you.
Thank you, Fabio. Can you hear me well?
Yep.
Okay. Good afternoon, everybody. I'm glad to see that so many of you survived the heat from the morning. Also, for I would like to thank the organizers for putting together the conference and for giving me the opportunity to talk. Today, I would like to tell you about causal maps in quantum field theory, or the problem of identifying the set of causal maps in quantum field theory. This is work in preparation, so any feedback or comments are more than welcome. And also, I have to acknowledge that a huge part of it is very highly inspired by previous work by Leron Borsten, Ian Yap, and Graham Kells. Okay, so without further ado, you can hear me? Oh, like, so can you hear me correctly? Or should I? Yeah, okay, perfect. Thank you for telling me. So I was saying that a lot of this work is also inspired by previous work by Ian Yap, Graham Kells, and Leron Borsten. Okay, so without further ado, let's start from the beginning. The reason why I care about this problem is because I care about measurements. We've been hearing a lot about measurements this morning. Well, the reason for this is because for a physical theory to be useful, we need to be able to describe how we extract information from the physical systems that theory models. And in physics, we usually do that with measurement theories, which can be either derived fundamentally whenever the measurement process can be described from first principles, or they can be prescribed. But in any case, they should at least fulfill these 4 principles. They should produce definite values, because ultimately in an experiment we always deal at the final stage with classical information, so things that we can write down in a notepad or represent in a graph. It should incorporate an update rule, because not all measurements are destructive, and the measurement theory should be able to tell us what's the state of the system after a measurement has been performed. It should be consistent with the theory, in the sense that the measurement theory should not allow processes that are forbidden by the theory it is attached to. And finally, last but not least, it should reproduce experiments, because we want to use that measurement theory to model the actual measurements that happen in a lab. Now, as we all know, we don't know how to describe quantum measurements from first principles, but we do have a very successful and satisfactory quantum theory of measurement, where operations are described by completely positive non-trace increasing maps that can also be described by their adjoints, which are also completely positive and satisfy that inequality right there, which becomes an equality whenever the map is also trace preserving, which is when we call it a channel. In that case, the adjoint map is completely positive and unital. Now, in that context, general measurements are represented by effect valued measures, where every Borel subset of the set of outcomes is associated with a positive semi-definite operator, so that the probability of the subset is given by that generalization of the Born's rule. And finally, instruments provide the unnormalized post-measurement state of the system, which you can always normalize divided by the trace, and that's it. So this is a very satisfactory theory of measurement we have for quantum mechanics. So if we're interested in measuring quantum fields, the first thing that we should do is, okay, can we generalize this? And at first, it looks like you might be able to, because in general, a transformation of a quantum field can be described by a unital completely positive map that takes you from a sister algebra that describes the field to a potentially different, in principle, sister algebra. And if now you take it to two pure faithful states, then you can define this adjoint, this map that goes from the representation of the first algebra into the representation of the other, which is a subset of the bounded operators of a Hilbert space. And now by Arbeson's extension theorem, you can extend that completely positive map to a unital completely positive map that is defined from the bounded operators of a Hilbert space into the bounded operators of another Hilbert space. That already looks like the channels that we are used to and we like. Well, maybe except with the exception that this map in general is not going to take density operators into density operators, but that's a subtlety that we're not going to care that much about now. So in principle, say, okay, we are in the setup that we had in quantum mechanics. This is not different in any way. We have completely unital, completely positive maps from the bounded operators of a Hilbert space into the bounded operators of another Hilbert space. We should just apply the quantum theory of measurement that we have. And here's where we see that this is actually not possible, because Sorkin, as Chris Fuster mentioned in his talk, pointed out in 1993 that there are impossible measurements. So in principle, if we accept all this family of measurements that I just used, then we are going to have situations in which, for instance, here A and C are performing some operations, and then B is performing a one-rank measurement along a Cauchy slice that intersects with the future of A and the past of C, in such a way that even being a non-selective measurement, this operation is going to allow fast and light signaling between A and C. Now, this is against relativity, and it doesn't satisfy the third requirement that I said. So for instance, so this sort of measurement should not be allowed. So our measurement theory should not include this sort of thing. Now, of course, the first thing that you might say is like, well, but this is very unphysical. I need to have control over a whole Cauchy slice. We should discard those. You should actually only focus on localized channels. I was like, okay, sure, let's do that. How do we describe localized channels? Well, in principle, we're going to say, this is going to sound a little bit abstract at first, but then you'll see it's actually very simple, that the channel is localizable in a set L if every restriction of the adjoint channel, of the adjoint map, to the local algebras to the local algebras of sets in the causally in the causal complement of L is an isomorphism between that algebra and the corresponding local algebra for B. Now, this looks a little bit weird, but in any case, if you assume also Haas properties, also, I have to say, implies already that the image of the local operators of L are taken into the local operators of L for the corresponding algebra B. This is interesting because sometimes this condition is imposed when you define localizable channels, but it's actually not necessary because it's already a consequence of the first condition. And in the particular simple setup where A and B are the same, then you get the actually intuitive definition, which is that phi dagger, when restricted to the operators that are in the causal complement of L, should just act trivially, like the identity. Okay, so that is reasonable, right? Like a channel that is localized should not affect the observables that are in the causal complement of the region that is localized to. And in particular, it was funny because one case in which this is true, right, is when the cross operators of the channel are in the algebra of L. And I found that in fact this is the only in the case where the channel is weakly continuous. This is the only type of localizable channel. So you have that a channel is localizable when it's weakly continuous, if and only if its cross operators are local local observables of Earth. However, then I realized that this was already mentioned by Werner in 1987, so I guess I was a little bit late to the party. But in any case, these are localizable channels. I have described them. Can we move on? Have we solved the Sorkin's problem? Well, we haven't, because even if we restrict ourselves to localizable channels, we still get situations where A and C can communicate superluminally. So we still have non-physical maps. We have to keep going and purge a little bit more. So we have to describe localizable causal channels, okay, not only localizable ones. Now, in order to do that, let me first remark that in the Heisenberg picture, when we're working in non-relativistic quantum mechanics, what we do is that we're taking essentially operators from after the measurement to operators before the measurement. And in quantum field theory, that's also what happens. We are taking operators that are outside the past, in the out, what I'm going to call the out region. This is not original for me. It's in a lot of previous papers, in Chris and Rainer's, for instance. Two operators that are not in the future, so that the region I'm going to call L in. So that the natural way of understanding the adjoint map is as a map that goes from the operators in the out region into the operators of the in region. Now, given that, how are we going to define causal? Because to discuss what are localizable causal channels, first we need a definition for what is a causal channel. Now, for the case of a real scalar field, because that's the one that I'm going to restrict myself to, what I thought was, okay, let's go back to just PDEs. In the case of partial differential equations, we understand the solution is causal whenever we are able to describe the value of the solution in terms of the values and the derivatives of the solution in a particular Cauchy slice of a point, right? However, here I don't want to talk about derivatives. So what I'm going to do, I'm just going to make that region thicker so that I can just work with the values of the function, because whenever you have the values in an open region, you can always compute derivatives if you want to.
And from there, I'm gonna get my definition for causal. I'm gonna say that a map is causal once it's localized in L, if for every G compactly supported and smooth whose support is in the out region, and every open set in L in that contains a Cauchy slice of the support of G, I have that the image of the exponential smear field is in the local region, in the algebra of the local region O. Okay, it's gonna be my definition. Now I have now that I have a definition, I can go on and characterize what are the causal channels with a series of equivalent conditions. Now the first one that we find is that, well, we can just take the limit of what I just said and find that whenever we have a region in the in region and an O2 in the out region, so that O1, the region, the set in the in region contains a Cauchy slice of O2, then it has to be the case that the image of the local algebra of O2 has to be included in the local von Neumann algebra of O1. All right, this is actually analogous to proposition 3.1. Okay, thank you. To proposition 3.1 in Chris and Rainer's first paper, which is the proposition that then they use in impossible measurements requiring possible apparatus to show that in their framework there are no causality violations. So this is consistent so far. The definition of causality seems to be okay because it's leading to something that is being used in the literature to prove that something doesn't lead to impossible measurements. And the other condition that we get is that for all Fg like in the picture, so that the support of F is in L in and the support of G is in L out, and they are space-like separated, this has to be fulfilled. Okay, the commutator of the e to the I phi F and the image of e to the I phi G has to be 0. This already looks like a non-local, like a no-signaling kind of condition, and it also can be rephrased like this, saying that the image of e to the I phi G is not affected by the application of the unitary channel that is generated by the phi F. All right. And I can use this condition to define a signaling index, okay, which is just the subtraction of these two terms that should coincide and then applying a particular state eta. So I can define this upsilon eta phi that is just the supremum of that difference over all the F and G's that have L2 norm less or equal than 1. Now this index is nice because first of all it's a faithful witness of the causality violations, in the sense that assuming that the states are separating, if the channel has indeed causality violations, there is going to exist a state for which this index is non-zero. And if the index is 0 for all states, then the channel has to be causal. But not only is a witness, but it also serves as a quantifier, in the sense that whenever the channel is not causal, it also tells us how not causal is. And this has applications, for instance, in particle detectors, because as you may know, particle detectors do have some degree of causality violations, but we can show, for instance, that this new index is always going to be over the lambda square. And in general, if you put more parameters, you can tell at what order in perturbation theory the causality violations are going to show up. So it allows you to say how big the causality violations are. And then, for instance, you even have that some particle detector models are like the gapless and the Dirac delta couple detectors are actually perfectly causal. And then there are also no saline conditions. The first one is just the limit of the continuous limit of what I just said. But there is also, which already resembles a no signaling condition that Laurent Borstein and Job and Ryan Kels formulated. And you can show that they are also equivalent to a couple of no signaling conditions that Ian Jia formulated, which has a more operational flavor because it's actually just telling you that the image of some operators should not be affected by operations that are performed in regions that are space-like separated from those. In any case, I'm running out of time, so I'm gonna go a little bit more quicker. I just wanted to show the most trivial example, which is actually something that mostly already do in previous literature, which is the case in which you have unitary channels that are generated by a function of smear fields, and then you can use these results to show that the only case where this thing is causal is when the function psi is linear. And this in particular implies that channels that are seemingly not very problematic, like the one generated by the square of the smear field, is going to be unphysical. This was already pointed out in the literature before. There are more interesting examples, but I don't have time to show them, so please ask me if you're interested about it. And finally, a small remark is that these conditions are equivalent to that thing generating a star algebra that satisfies the AQFT axioms. And maybe, I don't know, but maybe this is a hint towards what the most general causal maps are, and maybe how they are related to, for instance, measurement schemes of the FP form. And I would love to talk about selective updates, but I don't have time. So yes, I'm going to refer you to Eduardo's talk on Wednesday morning. And that's all. These are my take-home messages. I just wanted to show you that the measurement problem has an extra layer of complexity in quantum field theory because of the relativistic constraints, that the class of localized causal operations can be characterized by a series of equivalent conditions, and that we also can define this signaling index that provides a faithful witness and quantifier of the causality violations induced by a channel. Thank you very much for your attention.
Thank you very much. So last, the next speaker to come and start, I will take one question.
Yeah, and so like the tower was the assumption that is there's causing the solvent.
The assumption of causal convexity
Yeah.
for the region. Well, it's more for convenience than anything else, because actually you'll see that I call them localizable, because in the end, when you're putting conditions for the causal complement, there is a handful of regions that have the same causal complement. So in the end, it really depends whether you call it localizing a specific regions or not. It really depends on how you're implementing the operation too. So basically, the causal convexity is because, well, you can always consider in general the causal whole of the region you're implementing your operations to. You can work with that. Also, in principle, by definition, the causally convex sets are the ones that we assign local algebras to for the same reason, essentially.
So in solving not for example, it's wide it can not.
Well, no, but you can still pick a region that is small enough and it's also causal convex. So that's not, yeah, the causal hole is going to be, well, you could, but the thing is that even with a region that is not particularly wide, you still get violations. Sorry, maybe I'm not understanding your point. We can discuss later because I feel like I was a bit in a rush.
Okay.
Thank you for your question. Thank you.
And our next speaker is Daniele who will tell us about quantum scalar and vectors of developing processes.
Sì, perfetto. Vabbè. So, this one? Okay. Okay, so thank you very much. I shortened a little bit the title, just evanescent particles. And I'd like to point that this is a work in progress in collaboration with Robert Tuckel and Adamante Zampelli. Actually, Adamante is here attending the conference. And okay, so the plan of the talk is a little bit maybe too optimistic, but anyway, I will introduce an alternative formulation to quantum theory, which is called the general boundary formulation. And I will present some of the application, in particular concerning the vacuum state. I will spend some time on the vacuum state. Then pass to the quantization of evanescent modes. We will call this quantization of evanescent particles, and a proposal for the time operator. And I finish with the vector field, the electromagnetic field, and some conclusion. So the motivation for introducing a new formulation of quantum theory, in particular quantum field theory, is based mainly on the problem of quantum gravity, which is still an open problem despite all the efforts and the approaches, but also on certain limitation of quantum field theory. In particular, here I put some in case of a ternary interaction, and we have to apply perturbative techniques, and then we have to rely on certain isometry to define, for example, the vacuum, and there is some issue concerning the quantization of evanescent modes. So it's not really showing the gray part anyway. So what one would like to have is a formulation which is fully local, not just in time, but in space-time, and moreover can solve some of the difficulties of the standard formulation of quantum field theory, and maybe have the appropriate arena for the formulation of quantum gravity. So let me give you just the general idea of this formulation. This is a generalization of the transition amplitude. So in the standard Minkowski-based quantum field theory of state, defined at an instant in time, or if you want on a flat space like hypersurfaces, and there is a unitary evolution in time. When we go to a curved space, things becomes a little bit more complicated because we can have different notion of time and vacuum, and in general, the evolution is not unitary. And now we want to generalize this as much as we can. So imagine we have a region where dynamics takes place, this blue region with some boundary, and then we will have states defined on the boundary. Okay, now this will necessarily introduce some generalization of the notion of transition amplitude. And the way to do it is to use the framework, the mathematical framework of topological quantum field theory, where we associate algebraic structure to geometric one, and in particular we will consider two geometric structure which are hypersurfaces. We consider oriented manifolds of dimension d minus 1. D will be the dimension of the systems in study, and wild regions, which are simply oriented manifold of dimension d, and we associate Hilbert space to hypersurfaces and a map which will generalize the notion of transition map to regions. And to describe observable, we can introduce another map, which we call observable map, and we put a set of axioms that make this association coherent. And to extract probability, we generalize the Born rule. So this framework actually has been applied for some years already. Let me just point out the first two papers, which are the foundational paper introduced by Robert Tuchel, which is the father of this approach. And the interesting thing is that the description is fully local in space and time. We do not even need a breakdown metric for this formulation. And it has been applied in many situations, in particular situation where we already know the answer essentially, but this GBF will provide a new perspective and also solve some of the problem which are listed there in the bottom part of the slide. So let me start with the vacuum state. So generally, to define the vacuum state, what we need is find a subspace which is positive definite with respect to an inner product. So the inner product is, do I have a point? Well, anyway, is the bottom line, and in particular, this is defined in terms of the symplectic structure omega, and it implies as the first entry is the complex conjugation of the field, and usually the subspace turns out to be a Lagrangian subspace. Lagrangian means that it is isotropic and coisotropic, which are properly defined again in terms of the symplectic structure. So if we go to the standard situation where we have a time interval region and we put an interaction inside the region is M. So we find that the solution of the Klein-Gudon equation, it's in the middle of the right part in the middle. Do we have a pointer or not? Maybe not. Anyway, so the solution, this eta solution of the inhomogeneous Klein-Gudon equation could be expressed in terms of the Feynman propagator, which knows about the condition, the boundary condition, and the boundary condition reduced to is such that eta reduced to the positive energy solution in the future and to the negative energy solution in the past. And these two spaces, these L plus and L minus, are indeed Lagrangian subspace of the space of solution. So if we want to generalize this, so we go to the right part and we apply the GPF, we will have a region where the subspace that defines the dynamic is a real Lagrangian subspace, and outside the region, which I call X, where we'll have definite Lagrangian subspace. And this definite Lagrangian subspace will give us the definition of the vacuum, which can be expressed in terms, for example, of the Schrödinger representation for field, combined with the path integral. And then we have that the amplitude in the exterior region, or the path integral applied in the exterior region, is really the vacuum that we can define on the boundary of this region. So in particular, just surprise what we get. We get an association, one-to-one corresponding between vacuum state, positive definite Lagrangian subspace, and boundary condition at infinity, spatial infinity or temporal infinity, or a combination of both. So let's apply this to a very interesting case, which is the upper cylinder, which is a tree-sphere in space extended over all of time. So this is an interesting region because the boundaries are at the same time connected and time-like. And moreover, the space of solution decompose into propagating and evanescent solution. And here, in the bottom right, I put the form of these modes, which are essentially spherical Bessel function. One is propagating and the other is evanescent. So if we proceed to the quantization of the propagating sector is really the standard quantization. In the Keller quantization, this really corresponds to the standard plane waves. But if we go to the evanescent sector, we know what is the appropriate boundary condition. We want that the field decrease at infinity, equals to 0 at infinity. So this will select a Lagrangian subspace, which I call Le plus. But it turns out that this is not positive definite with respect to the inner product. And the solution to this problem is simply to modify the inner product. So we introduce a new structure, a real structure with called alpha, which satisfies center condition. And in particular, we define a new inner product in terms of this alpha. So as you can see, the inner product again is defined in terms of the symplectic structure, but instead of having the complex conjugate of the first entry, we have the alpha transform, essentially because the evanescent modes are real functions. So if we take the complex conjugation, we do not invert the polarization. And moreover, if we look at the symmetry of the region, in particular this hypercylinder region, it turns out that alpha is unique. So we have one just choice, okay? Just one choice, and then we can implement I mean, we can find a substrate which is positively definite with respect to this inner product and start the standard quantization. And it turns out that if we do that and we compute a Feynman propagator in the propagating sector and the evanescent one and we sum, we recover the standard Feynman propagator Minkowski. This also be verified in all the spacetime. Okay, so now that we know how to quantize evanescent modes, now we can look at the physics of these modes, and we can do that by coupling the field to an Ur-Debye detector. And again, we put this Ur-Debye detector inside the hypercylinder. So we can study many effects. In particular, here I just represent emission and absorption of particle, and we can compute the amplitude, this rho amplitude, which will be the observable map, where the observable is the transition of the Ur-Debye detector from the excited to the ground state in the case of emission, or from the ground state to the excited one in the case of absorption. And let me just show you this this plot. So this is the emission spectrum as a function of time, and the mass of the field is set equal to 1. In the abscissa, we have the omega, the energy cap of the Ur-Debye detector. So on the right part, for omega larger than 1, we have the propagating sector, and this is essentially the standard result that we get if we use plane waves. But when omega is smaller than 1, the dominating part is given by this blue line, which is the contribution of the evanescent part. So if you want, this can be read as a prediction of this approach. If we make an experiment, okay, this is scalar field, so okay, it's difficult. But if we make an experiment, we should really see the blue line, not the red one. Okay. So it seems that these evanescent particles, well, they exist, they carry energy, they can excite and disexcite an Ur-Debye detector. And what we can do now, we can use this technology to define, to propose a time operator in quantum field theory. So the idea is to mimic what has been done by Newton and Wigner to define the position operator in quantum field theory. So the idea was to localize a state, a one particle state, on an equal time of surfaces with this proposal for the operator on the left. And what we did essentially is to make a 90-degree rotation of this picture. So localize a state on an hyperplane, which is defined at a fixed special position, x1, okay? So the form of the operator is written there. It's really, I mean, the analog of the Newton-Wigner position operator. But in this case, the quantization of this time-like surfaces implied also the presence of evanescent particle, okay? So if we compare the two, I mean, the quantization, I mean, and the probability density of the amplitudes for the Newton-Wigner position operator and the Newton-Wigner time operator, we see really an analogy. So we see two peaks of the probability density that correspond to classical trajectory. So on the right, we will have two trajectories that correspond as one particle moving on the left at an earlier time and then goes to the, this hyperplane of constant z, and one particle state moving in the right direction. Yes, in the right direction, and yes, other peak there, and then detect at z prime. But the very interesting thing is that if we separate the contribution between the propagating sector and the evanescent one, and we just consider the propagating sector, so this is the same plot as before, just rotated 90 degrees. So an unphysical divergence appear for the time separation, which is the abscissa delta t equal to 0, as if a particle created at that instant will immediately appear at another position, I mean, propagating at infinite velocity, and this is of course unphysical. But if we introduce the evanescent, we plot the evanescent contribution, which also diverge, but the divergence is negative, so there is a nice cancellation, and at the end we just have this red curve, where everything is fine. Okay, so it seems that, I mean, this proposal for the time operator seems to make sense, and let me just briefly conclude with the electromagnetic field. This is a real work in progress, so it's just preliminary result. Those that I will show you. So we consider three regions: the time interval region that we already know, the hypercylinder region, and something somehow in between, which is this waveguide region, which is a region which is bounded into special dimension, which we call here x and y. It is unbounded in the third, and it is extended over all of time. So in the first region, the time interval, the hypercylinder region, there is no evanescent modes. So the quantization proceed as usual. But in this tube region or waveguide region, there are evanescent modes. So now we know how to quantize these evanescent modes. And the result that I will show you is this one. We can study the dynamic by calculating the Feynman propagator. And we see that the Feynman propagator in the time interval region is equal to the one in the hypercylinder region. And if we compute the two contributions, the propagating and the evanescent one, to the Feynman propagator in this waveguide region, and we sum them, So we recover the standard propagator. Okay, so the region, I mean, this is just for a free theory, no interaction. But still, it seems that this quantization with this alpha map applied to the electromagnetic field seems to work and seems to reproduce non-dynamics, even in this way. So let me just continue. Okay, so so the GBF seems to be a valuable formulation for quantum field theory, and we see in also other applications that I didn't mention here that well, it works, and they can even solve some of the problem. For example, I don't know, the S matrix in anti-de Sitter and other stuffs. Here I just mentioned 3 applications, which are the vacuum, the evanescent particle, and the time operator. And maybe, I mean, just a note so far, it would be the proper arena for the formulation of quantum theory of gravity. So the way in which this can be further developed, it's there are essentially that we can do many things. So the first one is to explore more the physics of the evanescent particle, and we are actually working in collaboration with Damante Zampelli in order to study the interaction of 2 Moore-David detector in this hypercylinder region and recover some 2-point functions on known facts, also comparing the contribution of the propagating and evanescent sector. And then we can also study this evanescent particle, and in particular the localization of states in more general hypersurfaces. And there are some preliminary results in a cosmological model, which is based on the third quantization framework, which seems again to implement these evanescent modes. And yeah, I just put linearized gravity because, well, we didn't start to do it, but it's something I want to look at. Thank you for your attention.
Thank you very much. Any question? I can ask the question. So when the next speaker comes down. So in the general boundary formalism, so you always have assign your boundary conditions for your algebras to these space-time regions, which is, as I understand, are well-defined, sharply defined boundaries between space-time regions. I'm wondering, do you think there is any conceptual tension between this approach and quantum gravity, one thinks that to some extent space-time might make these sharp boundaries unavailable, or do you think it can work with that?
No, I hope there is no tension. And also, not so sharp boundary I've been considering. Then you have to modify a little bit the axioms. What is the explanation of the algebraic structure to this corner, essentially? I mean, we considered boundary with corners. And moreover, I'd like to also mention that this GBF is already compatible with some approach to quantum gravity. Particularly, well, gravity is just topological, so of course this is used to topological quantum field theory, but also in spin forms, and also I think also in this approach called group field theory. I think there will be a talk by Daniel Oriti on this. So it seems to be already compatible with some of the approach to quantum gravity. So I don't expect any tension, to be honest.
The silence 5 minutes and 3 minutes before the end of the questions. If you want questions, I can wrap up at 3 minutes.
Thank you.
Okay. Well, our next speaker is Max Fahn, and you can read the title. Thank you. Go ahead.
Yes, hello, and thanks very much to the organizers for giving me the opportunity to speak here today. I'm Max Fahn, and I'm a young postdoc currently working at the University of Bologna in the INFN Bologna. And today I will talk about gravitationally induced decoherence on scalar particles from field theory. So the setting of this entire project, which I did in collaboration with Christina Giesel at the University of Erlangen FAU, is that we have some quantum system of interest whose detailed dynamics we want to know, here depicted in green. And this system of interest is coupled to some rather large environment whose detailed dynamics we do not want to track in detail. Maybe they are too complicated, maybe there are too many degrees of freedom to simply store and process them. And then the dynamics of this reduced system, this green system of interest, is given by the so-called master equation, written here on the right-hand side. where rho s is the density matrix that describes the state of our system of interest. And here you can see without the red operators would just be the standard Liouville-von-Neumann equation. And these red operators depict the effective influence of the environment on our core system of interest. And these red operators can encode new processes, among other things, the loss of energy from the core system of interest into the environment, called dissipation in this framework, or also kind of the flow of information, or a bit more precise, the vanishing of the off-diagonal elements of our density matrix in some specific basis, which therefore means that the interference probabilities in the specific basis vanish. And therefore, one can talk about, roughly speaking, of a classicalization of this particle in a specific basis, and this is called decoherence. And in order to derive such a master equation, one has several possibilities. One is to start with the classical action or the Hamiltonian of the full system, including the environment, which consists then of the system Hamiltonian for the green system, the environmental Hamiltonian, and the interaction Hamiltonian that tells us how these two systems are coupled to each other. And this interaction Hamiltonian, when using quantum mechanical models, so particle theories, then this usually has to be written down by hand and guessed or find by trial and error or by analogy. However, when starting from a field theoretical point of view, for instance, from the standard model or from general relativity, then this interaction is already included in the theory. So general relativity tells us how it couples to matter, which is some nice feature we would like to use. However, when we start from this field theory, the complication arises how to get back to a master equation for just one single particle. So for instance, one single scalar particle, if this green system of interest could be a scalar field. And this is precisely where the talk is settled in this project. Namely, we consider a master equation from general relativity for linearized gravity as environment, coupled to some bosonic matter field. And such master equations were derived in these works here, where all of them have in common that they start from the classical action of general relativity coupled to some bosonic matter field. And then in this field theoretical master equation, the system of interest would be a bosonic matter field, and the red operators would encode the influence of this environment. In all of these cases, this would be linearized gravity, quantized in Fock quantization. If you want to know more about this first point, in that sense, more broad about master equations on gravitational-induced decoherence, also inspired with loop quantum gravity, then I can recommend you the talk on Wednesday morning by Christina Giesel, who will give a more overview over the more broader picture. In this talk, the aim is now to get the dynamics of a single matter particle out of this field theoretic equation. And in this work, such an attempt was already made in the derived single particle matter equations. For us, the motivation for this project was, however, that they found that all of these master equations contain divergences, which are somehow inherited by the underlying effective quantum field theory, QFT. And these divergences were treated in these works. On the one hand side, in some of the works here, for instance, not at all. And in the other works, they removed them in the end after performing other approximations at the quantum mechanical level. And we were interested in seeing whether we can remove them already in the initial stage, kind of immediately when starting with the field theoretical master equation, to see, in that sense, how these divergences connect to quantum field theory, how we can renormalize them following the procedures given by quantum field theory, and also then to have a renormalized one-particle master equation on which we can apply further approximations. That sense to also be able to study what these approximations mean physically. That is, which processes are suppressed by these approximations. And for this, the roadmap of the remainder of the talk is that we use the master equation derived in this work here, which has this standard form of the master equation for linearized gravity coupled to a scalar field. The assumptions, or some of the assumptions which entered, were that the coupling is weak between both systems and that the linear gravitational perturbations are thermally distributed in the environment. And then all of this is now Fock quantized effective quantum field theory. And then the idea is to perform in the beginning the quantum field theoretical renormalization of this effective quantum field theory to remove the divergent terms in the one-particle master equation already at the beginning in order to obtain a predictive one-particle master equation, and then perform further approximations on this master equation and in the end apply this to ultra-relativistic particles and as a toy model to neutrinos. Let's dive into some of the details. So for the quantum field theoretic renormalizations, the Feynman rules, which can be read off and derived from the initial Hamiltonian of the entire system, scalar field to coupled to linearized gravity, which in the work we refer to was written or expressed in terms of relational observables that encode only the physical degrees of freedom. And then one would obtain the scalar propagator, so a propagator for a scalar field with its momentum and mass, the propagator for the graviton field, which is massless, also has some momentum, and here P, A, B, C, D being the projector onto the symmetric transverse traceless physical degrees of freedom. So if you want onto the plus and X polarizations of the gravitational field, waves in the classical picture. And one can see here nicely that our assumption was that we do not only have a vacuum field, but we have the thermal distribution of this gravitational waves. So also the Bose-Einstein distribution enters here, which is moderated by some thermal parameter, some thermal temperature parameter. And then there's an interaction coupling one graviton to two scalar particles. And in the next step, the individual terms of the master equation were connected to Feynman diagrams, where this work here was of use, where they did such a connection for a scalar field coupled to a scalar environment, and then we extended it to apply it to a scalar field coupled to our linear gravitational environment. And from this, we could learn that the divergent terms in this one particle master equation come from the vacuum self-energy. And we could remove them by renormalizing the self-energy loop of our scalar particle here. And the effect of this renormalization then was to remove all the vacuum terms from the dissipator, that is from this red operator here. So in vacuum, this would now vanish only when there's this thermal distribution. So vacuum means setting the thermal parameter equal to 0. So the thermal state also encodes or includes the vacuum contribution. And with this renormalized one particle master equation, then in the next step, we applied further approximations. And the typical aim of these approximations is, on the one hand side, to obtain a completely positive master equation, which has some physically desired properties, and on the other hand side, simply to make it easier solvable from an analytical point of view, so to reduce its complexity. And the approximations which are usually employed in the literature are these two here. The first one is the so-called Markov approximation, where the idea is that the environment forgets rapidly about the influence of the system, or speaking a bit more physical, that the timescales in which the environment evolves are much faster than the timescales in which the system evolves. And for our case of interest, namely ultra-relativistic particles, later on we could indeed show that this is justified. This approximation works in this regime with gravity as an environment. And the second approximation is the so-called rotating wave approximation, which has beyond the idea that detectors cannot resolve arbitrarily fast oscillations, and therefore one can average over these oscillations. And for this approximation, we couldn't, unfortunately, not yet comment on the validity or not, so this is still an open point. And after applying these two approximations, on the validity specifically using gravity as environment, it is often used also in the literature in the master equations I quoted in the beginning, but still investigating further the validity and bounds of which system it's a good approximation, for which it's not so good at all, is still an interesting open point. Okay, after these two approximations, the dissipator has Lin platform, which is a very specific form you can see on the next slide if you're not familiar with it. And here the red additional term in the Hamiltonian parts on this unitary evolution vanishes. And then in our last step, we went into the ultra-relativistic limit. And if we go in one dimension, then it turns out that the master equation has specifically this form. And here the dissipator is of Lin platform. Sorry. And the only operator which appears in this dissipator is just the system Hamiltonian. This is kind of some consequence of the way how the coupling works from GR to the scalar field. And this agrees indeed up to a prefactor with a similar single particle master equation derived in this work here for photons. And you can see that this dissipator part here has this temperature parameter T and also knows about, of course, the coupling between gravity and matter. And a solution for this master equation in energy eigenbasis and assuming discrete energy levels Ei, Ej has this form here. So without the gravitational environment, this last term would vanish, and we would only have the standard unitary evolution with this phase shift Ei minus Ej times Et. However, if we include this gravitational environment, we get here a damping term, which is indeed minus something positive and linear in time. So with increasing time, therefore, the off-diagonal elements in the energy basis are damped and will vanish after waiting a certain time long enough. And to have some physical application of this, we applied this as a toy model to neutrino oscillations with the idea that the energy levels which we have here are equal to the neutrino energies in mass eigenbasis. And the form of this mass equation then indeed confirms an evolution predicted in this work here, where a quantum mechanical toy model was used ab initio. So a single neutrino particle coupled to an environment of harmonic oscillators to model the gravitational waves. And with this microscopic toy model and this confirmation here, one obtains an energy dependence of the decoherence effect in neutrino oscillations. If one inserts here the ultra-relativistic approximation for neutrinos, then it turns out that the decoherence goes with e to the -2, and this also provides a value here for the prefactor of this decoherence in order to determine the correlation length. With this, let me come to my summary. So the aim of this project was to access the one-particle sector of a field theoretical master equation for a scalar field coupled to linear gravity. And the motivation for this, starting from a field theory, was that this provides us with a natural coupling. So how to couple these two systems. And the main results are on the one hand side, the quantum field theoretical renormalization, which was starting from Feynman diagrams, gave an interpretation of the divergences that arose, and in the end, a predictive one-particle master equation before the application of further approximations. We also analyzed Markov and rotating wave approximations often applied in the literature, and one is also able then, following this route, to determine which physical processes are suppressed by them, and in the end apply this to the coherence in neutrino oscillations. With that, I want to thank you for your attention, and I'm happy for questions. Sorry, this one? Sorry, the acoustics is a bit bad. Could you repeat the question? The temperature. The temperature parameter, this enters here in the beta. So beta is 1 over kBt, so which can be seen here. And the idea is that we use a Gibbs state, kind of a thermal distribution for the scalar, for the gravitational particles in the environment. Yes, kind of we make an assumption for the initial state of our gravitational field, and this kind of we assume that it has a thermal state. Okay. Okay, thank you. Yes. So what we did here was that we only focused on the terms which appear in the one-particle master equation later. So on the terms which we are interested in, and this one-particle equation was obtained by the idea of dropping all the terms that would project out of the one-particle Hilbert space in the end, and we only go up to second order in the coupling and kappa. So kind of we can only have at most two vertices and want to start and end with a scalar particle, and then. I think so. If we, under these assumptions, we actually only got these
term, this one which we had to renormalize, and up here this one interaction term. So there were indeed no further interactions which we had. So there was no more graviton loop. Maybe because we can see. Quick. Yeah, Bruce. No, actually not. So we did not take the high temperature limit. We just took a general temperature parameters, can also be very low or even the vacuum. And yes, so we saw that for at least when we use ultra-relativistic particles, then the Markovian limit is anyhow justified, no matter which temperature. Not necessarily. So here indeed, maybe also for other kind of particles we didn't check, but for ultra-relativistic particles, it's justified for a general temperature. So this is thank you, but thank you. Okay.
I give you 5 minutes and 3 minutes for me to answer questions. Okay. So 3 minutes on I should cut it off. Okay, let's welcome our last speaker from today's session. Is Director Braccini. He'll tell us about probing gravitational entanglement.
Hello, everyone. And first of all, thank you for the organizer to organize this and the volunteers. And also importantly, I think everyone here listening that survived this tropical weather. And I don't know, it's nice to be here. And yeah, so I'm going to present a work in collaboration with my two main supervisors, Sugato Bose and Alessio Serafini. On entanglement and gravity experiment. And so to give an overall introduction to the topic, the original idea was that if you consider two superposed masses placed in a superposition of left and right, and you let them interact through the gravitational potential, they accumulated some relative phases, which makes the system entangled. While I will not go into the details of what implication has on a fundamental theory of gravity, I will instead focus on what are the underlying assumptions that this steps does, and what is the pathological issues that arises in this description, and how hopefully to fix them. So the overall idea is that these relative phases comes because the position of the particles are eigenstate of the Hamiltonian. And specifically, this does not include a kinematic term. And here we find already the first problem is that if we include the kinematic term, these states are not eigenstate anymore of the system. And this the assumption is that our state are infinite squeezes, are some delta functions of the position, and an infinite squeezing of the mass means that there is an infinite spread in the momentum from Heisenberg uncertainty principle. And this is an issue. And specifically, it's a bigger issue when someone tries to give experimental analysis of this experiment, because in the spread of position and momentum, all the noises of state preparation, Lindbladian noise, are encoded. So the question that I will try to answer today, is it possible to give an operational description of this experiment, and specifically a dynamics which studies a creation of a superposition of Gaussian states? And for this, we look at the literature, and on your right-hand side, you will see Gaussian states, and in particular, the application in sensing of entanglement, it's achieved through squeezing of the Gaussian state. While there is the original school of thoughts where this experiment was proposed, and experiments are trying to be made, is a creation of a superposition through the interaction of a levitated system with a qubit. And the question is how is it possible to extrapolate some lessons from Gaussian dynamics to superposition of Gaussian dynamics? And given the sake of time, I will try to, oh, sorry, I forgot this. So basically, in nature, there are very similar Hamiltonian arises in different contexts of quantum information. Specifically, of interest are the ones that are operated valued Gaussian dynamics. So one example is the Stenger-Luck interaction. This happens in electrons and V centers, both as a single quantum system as well as macroscopic one like levitated system. And this is an operated value force which displaces, for instance, a trap left if the state is up and right if the state is down. And another example of an operated value interaction is in the James Cumming Hamiltonian. And this represents a time-dependent resonator which interacts with a single qubit and represents the exchange of a single photon with a discrete level system. And it can be seen as a frequency shift in a trap, for instance. And this frequency shift appears in so many physical systems, for instance, a superconducting qubit, dopant spins, from IBM quantum computer to a very small lab in a basement somewhere. And the question is it possible to give a complete description of the arising dynamics, arising states, open and close with monitor or feedback of these operated value Gaussians? And this is what we have been working on over the past few months. It's still a work in progress, but close to completion. Hopefully, it will be soon out this summer. And I will try to give you at the same time some lessons from the Gaussian dynamics and how we generalize it to any superposition of Gaussians. And specifically here, I'm using a formalism introduced in this very nice book from my secondary supervisor, Quantum Continuous Variable, which I suggest if some people use Gaussian dynamics. So the issue is that Gaussian states of continuous variable are infinite dimensional Hilbert spaces. And specifically, if someone includes a qubit or a qubit or n qubits, you have an additional like C-squared Hilbert space. And one can define a vector of observables that encodes all the information of our system. And similarly, in our superposition, we can take the tensor product with the qubit basis. And interestingly, the commutator relations are the same. And formally, Gaussian dynamics are completely integrable. And given the structure is held as well in the superposition case, we can find some cases where it's also generally integrable. We can choose a basis. There is a preferred one, which is the displaced operator basis to represent operators acting on our Hilbert spaces. And then for the qubit, we have a preferable basis from the interaction type that we are describing. And given a density matrix, we expanded this in the qubit basis. And then we can define a characteristic function. From the name, this function is characterized fully a quantum state. And one can define the phase space representation of a Gaussian state. Similarly, here we are defining a superposition of phase spaces and Gaussian states. From this, it's possible to define a vector of expectation value and a matrix of expectation value in the Gaussian state, in the Gaussian case, which fully described a Gaussian state through its characteristic function. Similarly, in the superposition case, we have a list of vector and a list of matrices which encodes all the information of the superposition. And we arrive finally at the central definition of my talk and the state that we are considering, which is we call the Gaussian cat state, hence my cats at the beginning of the talk. And those are solutions of a very large set of Hamiltonian, but they're still solution as well of open quantum dynamics, monitored and with feedback. Specifically, one can find easily the reduced density matrix, which encodes all the information that our qubit, the qubit has. And this gives a dynamical description of the evolution in terms of a set of ordinary differential equation, which describes the evolution of our phase space variables, the covariant matrix, the first moments, and this additional scalar that I call R0, which encodes the phases and the contrast that the qubit has. And let's try to build an intuition of this superposition of phase spaces. This is an example of one qubit and one mode. So on the diagonal term, we have two Gaussian processes. So if someone discards the qubit and you trace it out, what you get is a statistical mixture of two Gaussian processes, which is a fully classical dynamics. However, if someone measures, I don't know what happened. Okay. If someone measures the qubit, interference patterns arises, and the state collapses, for instance, the plus state, and in the minus state, and Wigner negativity arises. And what I've been plotting here is a Stenger-Luck interferometer. This is when this operated value, a qubit gives an operated value force to a trap mass. This is predicted to happen in NV centers. They're magnetically trapped in superconducting flux qubit with a magnetic trap, and also in atom with pole traps. And now the question that arises is, can we take two copies of these and try to understand the entangling dynamics between two of these sensors? And to do so, I consider a general potential, but in this case, I'm presenting only gravity. You expand it to the second order in order to include Gaussianity, remaining to the Gaussian regime. And the superposition, given that now we have two qubits, are 16 phase spaces. Each of them is 4-dimensional. But still, given that the coupling between the qubit and the continuous variable systems is linear, because the Stenger-Luck interferometry, this dynamics is fully integrable, also in the open dynamics case. And so one can try to quantify the amount of entanglement present in the qubit and measure the partial transposition criteria under measurements of your qubits. And specifically, one can find the entanglement phases and the contrast that by sensing the entanglement may decrease. And this, I want to note that just by the action of measuring with another Stenger-Luck interferometer the entanglement, you will lose visibility in the measurements. These are the contrasts. And specifically in the phases, we can ask when the entanglement is maximized or when the phases are equal to 1. And in this specific case, we find that the scheme is mass independent. And so this may be useful for experimental apparatus, as this is trapping a big object. It's harder. However, most of the time, forces in nature that couples continuous variable with qubits are very small. And so actually, this is where everything started. We were trying to find a dynamics, a Gaussian dynamics, which delocalize as initially small superposition. And this is done by some instabilities or inverted potential, which are starting to be quite widespread in literature. And we show that the displacement, the superposition increase exponentially faster, and the sensing property of this interferometer is exponentially better. And also both for sensing as well as entanglement. So to conclude, Gaussian cut state can be formally described by a superposition of phase spaces and through their first and second moments, superposed ones. And then entanglement can treat it dynamically, analytically, and detected through local measurements of the qubits. And finally, the exponential expansion can be derived. And with this, I would like to thank you, and thank you for holding until the end.
Thank you very much. So, for quick question, maybe I have one. So, you're using all the formalism of Gaussian states, assuming that you can prepare Gaussian states and get states and so on. The real system might not be exactly Gaussian. So, sensitive will be entanglement weakness to non-Gaussianity. Do you have any control of that?
Experimentally, it's quite hard to build non-Gaussian states, as like nature gives us classical states are
Gaussian.
to prove that something is Gaussian. What do you mean?
Exactly Gaussian. I mean, if something is epsilon not Gaussian and you don't know,
Yeah.
can you still?
I'm not sure. I think like the non-Gaussian part will be not analytically treatable, and probably like you should pass through like some perturbation. But generally, nature you start from a classical state, and then like it's very hard to build like a non-Gaussian one in general. Yeah.
Hey, let's thank you. Back to Peter.
Thank you very much. Potrebbe essere come dire, basta solo start at 15 minutes, maybe 15, but to do that, basically we have to squeeze a bit the consequence and the launch pad, but we would like to do this fire because we believe it will be very quick. Send it an email, very simple. We are doing it. You will be the awesome.